1, 2, 3, 1, 2, 3.
That works. Hello, hello, hello. Hello, hello. Take your seats, please. We're about to begin. Right. So my name is Lukasz Wyrzykowski, and I welcome you here on our next, already the 14th Gaia Alerts and ORP Time Domain workshops. There's been a long road until here, but we all made it to beautiful Malta. So thank you all for coming. Thank you all for joining us online. You will not be able to see me now because we don't have camera here, but I hope the sound is more or less okay. So I only have a couple of technical announcements before we begin. The Wi-Fi password is here, but don't use it if you don't really need to, okay? Because it will slow down our Zoom transmission on YouTube. And like as you noticed, there are no tables, so you're not encouraged to do your work, which is great. So you're encouraged to listen carefully to what is being said, unless you're working on your presentation at the last moment. That's allowed. Okay, so this is the Wi-Fi, which I don't encourage to use. Then, as I said, we are Zooming and we are streaming on YouTube. Everything what is on this screen, I hope, is also being visible on YouTube and is also being recorded. So if you don't want that, let me know. But typically, of course, you might not want that. So if you clearly don't want this, then we can shuffle the schedule a little bit, so you'll be the last of the session, so that we don't need to interrupt the whole sequence of recording. But I hope it will be useful for also for you to look back at the recording. So the links to YouTube are already provided in the agenda. Link to Zoom has been sent to you, and also it's on Slack. And I encourage to use Slack. For that you need Wi-Fi, okay? To communicate with us, and also especially with people who are on Zoom. There's another 30 or even 40 people on Slack. So in total, there's something like 65 people who are actively attending this conference. Okay, so as you see, I'm using this microphone, and I encourage all the speakers to use the microphone while here, because unfortunately we need to record the sound which is coming from these speakers, then it has to enter my microphone on my laptop, and then it gets recorded. So keep that in mind so that people can hear us what we say. So this is a microphone which we can use in the room as well. There's another one here, which you'll also encourage to use if you prefer. There's this red. If it's red, it's wrong. If it's green, it's good. I think we have another one of these, right? No? Just one. I see. So we'll have to come up. How do we do with questions, right? And also for the questions, wait for the microphone. Or unless you're very close to my laptop, then you can shout. Probably that will work. What else? Wi-Fi and toilets. These are two main important questions people always ask. So I was told that the exit door behind you is the toilet exit as well. So make sure you're aware where the exit is. But note that this is only one-way entry. So once you leave, you cannot enter. You have to go around. What else? Any other technicalities?
Password. Yes.
You're not encouraged to use it. You can use your roaming, of course. Right? Anything else I've got? If not, then it's time to start, I think. I think that's it, yes? Okay, Gerry, can you? I'll switch on your... I will. Right. You can start speaking. This is some complicated engagement. It is, it works.
Just a sec. So that's this, and I'll make it big. Right.
Okay, good afternoon, everybody. It's a pleasure to be here yet again at these Gaia Alerts and related workshops. We've come a long way together. And so what I'm going to do today is summarise how far we've come and how we got here, and then look a little to the future, because the future is different than the past. And so the first note is this is a talk by myself and Gudrun, who's over in the corner there. I think you probably all know her. Could you stand up a bit, Gudrun, just in case there's someone who hasn't met you yet? Gudrun does all the work for these projects. And the other key thing, of course, is we're talking about EC-supported TNA and TDA, which is the money that's in the background, and that's the focus today. But I'd like to start with this little poem, which you can read, but for those online, it says, "They said it could not be done. With a laugh, he went right to it. He tackled the thing that couldn't be done and couldn't do it." Now, I put that on my desk when I arrived in Cambridge for the first time, a very, very long time ago, just to be in the same situation as the person standing behind the Roman general when he won a victory, reminding him that life was short and he might not be there tomorrow. And so not to get too confident about things that might always be. And this will be the lesson that we get to at the end, that there are things that we can't always do. Anyway, there's a heck of a lot we have done. And so where are we? And so the background is, for this EC funding of this program, is this combination of programs, Opticon and the modern one, ORP. And so Opticon and RadioNet were first funded nearly a quarter of a century ago, so a very long time ago, at the end of what at the time was called Framework 4, the beginning of Framework 5. And the idea was to develop EC support for European astronomy, and particularly, so that was technical support, that was most of what we did, but also to deliver open access to observing facilities. It was an entirely new concept at the time. Most of you won't have any memory at all of what the universe was like a quarter of a century ago. You're all in swaddling clothes at the time. But in those days, telescopes were national facilities. They were national treasures, and you had to belong to a national community to get access. And we've become a bit spoiled with things like ESO and Opticon RadioNet access since then. But at the time, there was very little. So we created it. And so these programs developed into what the European system called Integrated Infrastructure Initiatives. And the whole point was that they delivered an integrated program. And the key parts of that were, first of all, networking, so building the communities. Because remember, a quarter of a century ago, Europe was just rediscovering itself after the fall of the wall, and it was around the time of the end of the Soviet Union, and so on. Things were changing dramatically. And so the idea of the networking was a really key thing in those days, getting to meet and talk to people. There was also a huge amount of effort put into technology R&D, trying to catch up with North America and everywhere else. And then there was this thing of TNA support. And TNA support was always a big deal in radio astronomy, much bigger than for us. But we developed this concept of a common time allocation, so that resources were put in a pool and everybody in Europe could compete for them. And that was a totally new concept. It is, so far as we can tell, not been adopted by any other community in any other subject in Europe. So this either means it was a very good idea or a very foolish idea, or you can decide for yourselves what it was, but this was created and is still in place. And the EC liked it, and they said, well, this is an obvious way to do it, let's act like Europeans. Oops, I knew this thing was going to be too complicated. You have to go more slowly. Right, one little click. Got it. So this is the summary history of Opticon as it was, starting back in the year 2000. And as you can see, it grew and eventually had quite substantial budgets. And most of what it did was hardware, technology development. Overall, it involved a very large number of people across Europe and beyond. And these were the main observing access and technology and networking and things, activities that we supported. A key person in it, I'd like to mention explicitly, is Dr. John Davies, who was the project scientist who retired yesterday. So it's the end of an era. He was there all the way through. He's now retired and moved on. Gudrun's been there for, well, it seems like decades, but it's probably only one. So this is just a summary of some of the things. There's just a couple of slides doing the history here of what came in the background. So a very, very broad, ambitious set of schemes, of which time domain astronomy, setting up a time domain astronomy community was only one among many, because all of these things were just being created in Europe at the time. There's also some very ambitious technology developments and some very sophisticated implementation. And so I note particularly the Sphere facility, because that reappears on the next slide. It was an example where Opticon, over about 15 years, developed the high order adaptive optics technology and built it, and so provided about a quarter of the total structure of the Sphere facility at the VLT. Now that was just one of the many things we did. And the impact of that you can see in this text up the top here, which is from the US Decadal Review, not the most recent one, the one before that, in which the US National Academy of Review said basically the ESO system allows it to plan efficiently for future instruments such as the Sphere spectropolarimeter with high contrast adaptive optics. And that was picked out as the world-leading example to which the US could not hope to compete. And it's still true, 10 years later, the US has not been able to come close to competing with that sort of thing. And so then there was another thing it picked out, which was the EELT, which again started off as an Opticon project. And so I was the first project scientist for that. And so these shows the global impact we were able to have, but of course most relevance now is the time domain stuff, but there's also a lot of other impact. This is a slide I was given by the people from Strasbourg, showing the consistency of Opticon over the decade and the various European funded software technology development projects that have gone through all of that, and the various strategy documents that have gone through the whole thing as well. And so we were the backbone, allowing all these other things to develop further in the way they did. This I just mentioned briefly. This started as one of our projects and is now halfway to completion. And this, of course, is the bit that's relevant now, is this other network that was being built over the last decade, led by Lukasz, whose name keeps changing and getting even harder to pronounce every time I see him. I thought I'd had it about right a couple of years ago, but he's changed it since. But anyway, you can see there's this total global network of small and mid-sized telescopes, which is now in existence and operating. And this has been one of the great triumphs of how it's possible to get people to coordinate if you provide some basic resources. And this was the more general TNA access program running up until the very present. And so up and right until now, there is still access on 4-meter class telescopes, lots and lots of smaller and robotic telescopes, but also complementary work on VLTI and adaptive optics test beds and so on. And so all of these things are currently underway. And these communities are continuing to be supported. There's the community adaptive optics expertise. This has become critical mass and is now very successful. There's an organisation called the European Interferometry Initiative, which is smaller, but they're the people who do the optical interferometry, and we provide core underpinning for them. But the highlight here, of course, is time domain astronomy and providing some underlying resource to provide development and coordination and training schools to do the whole thing. Now, after Opticon, what came next was this thing called the Opticon RadioNet pilot. Now, this was a move by the Commission. This is the current state of the art. A move by the Commission to merge communities into bigger consortia, largely from their perspective to both reduce administration, so if you've only got one contract instead of two, it's easier for everybody in theory. But secondly, to enhance interdisciplinarity. This is the buzz phrase that everybody's interested in, and so obviously radio astronomy and ground-based optical astronomy are similar to an outsider anyway. And so it's got to be a good thing to bring them together. But what they did when they did this was remove all the technology development and networking resource and say ORP is just focused on access to facilities. And the second critical feature, which was strategy. So defining the EC astronomy interface. So we do two things, basically. One is deliver access to facilities. That's just a money transfer thing largely. And the second is try and plan for the future. And that's the bit that's proving more interestingly challenging. So this bit of ORP you all know well. This is what we're here for the rest of this week to talk about, is the time domain astronomy. So this is the main part of it. This works, this exists. This is where all the action is right now. And even for another 18 months or so, continuing as Gaia follow-up. As Gaia's going to last till February 25, February 25, so it's got a bit to go yet. And so there's this system, and then the other time domain astronomy activities. So this is the global stuff. So it's still possible, and there's substantial amount of effort put in through the CTAP. So open proposals put in by everybody for all these bigger telescopes. So these are these ones here, right up to SALT. The really big thing, and the networks around. So one can just apply for time on these things, and people do. It gets a lot of time through the CTAP process. So this is naturally complementary to the BHTOM process. And then the third aspect, which is of some relevance, but is going disappointingly slowly, was to develop a single point implementation of multi-wavelength proposals. So that you could write a single proposal that would give you access to as many different radio facilities, optical facilities and infrared facilities as you want. And so instead of applying for a different TAP for every single facility, you would just write a single proposal for the science. And so you would implement something similar to what is done on BHTOM, but on all the world's other facilities. And this continues under development. It's late, but I hope it will still happen. And it's likely that TDA will be an early test case of this if and when it arrives. So the other thing, of course, that we are supposed to be doing is strategic planning. And here that we have some challenges. The first, and it's not written on the slide, but the first and most obvious is that the personnel in the EC change. Not surprisingly, after 23 years, some of the people have gone and new ones have come in. And in particular, the recent wave of changes have brought in people with no background in infrastructure, processing and support at all. And they're doing things differently than their predecessors did, largely. And so the current process in the sciences is heavily delegated to what is called ESFRI. This is the organisation that looks after very large-scale facilities. And it's a sort of it's a EC-supported, but basically intergovernmental organisation that looks for the really big projects and decides or prioritises them and sets them up in a way that they can be given national support, because the national agencies have to pay for them. And so the ELT was one example of the things that went through that. The SKA has been through it and has been built, and the Cherenkov telescope array has been through it and has been built. And they're the obvious big astronomy things. But these are mega, these are billion euro plus scale things, and with time scales of decades associated with them. And the complication there is the sort of structure and policy and planning that is relevant for a new facility that will come online in 20 years' time is totally different than the day-to-day operation of facilities that are actually used by people today. And so balancing continuing support in the short to medium term, for existing small facilities, which will never be up into the mega national scale budget cost, is very hard. There's too much of a dynamic range here, and the EC used to operate by getting coordinators of all the projects together for a couple of days every couple of years and got an update from us on what we needed. But then they've stopped doing that. And they've focused very much on these big high-tech things. So for example, the technology development call, the one that's open now, requires that you must focus on a minimum of 3 S3 scale facilities. Now in optical astronomy, there are only 3 S3 scale facilities, right? 3 is the total. Radio astronomy is about the same. So this naturally is biasing what one can do away from what might be of relevance to the majority of facilities. And so planning and informing people of majority needs is hard work, and frankly we're just not achieving it. The communications are not in place. I've been trying for months to get ORP to set up meetings with the Commission and actually go and talk to them, and for reasons that we don't need to go into now, we are failing to do this. It's not been done yet. Oops. Wrong. That was that, right? I hate this thing, Lukash. I hate it. Right, so what's coming next then? Well, as well as the EC set up 3 of these pilots. Opticon RadioNet is a pilot. There's one in atmospheric chemistry, and there's one in materials fabrication for nanostructures, not nanostructures, but nanoscale production. And each of these things, each of these pilots was asked to come up with a strategy for their type of community. So in our case, it's people doing basic science on small and moderate sized facilities, minimal, if any, commercial elements. One was the chemists, where their challenge is that literally every chemistry department in every university in Europe has got a relevant chemistry group, and so there's tens of thousands of groups, and how do you decide how to manage it? And then there's the nanofabrication, with challenges that are linked to commercial and industrial applications. So we're supposed to be talking to each other, and we do a little bit, but we don't actually have very much in common. There was recently, the most recent call from the Commission for supporting astronomy was a call for what they described as multi-messenger astronomy. Now, multi-messenger astronomy, we all understand, it's a follow-on from gravitational wave detections, and more recently the beginnings of high-energy neutrino detections, and in the future there'll be high-energy cosmic ray detections more regularly. But this call was developed entirely from the particle astrophysics negotiating side of the system, and there was no contact or input from astronomy at all, even though this call for the future of TNA, i.e. us, was supposed to be about astronomy. So our future was actually decreed by people who took no notice of us and didn't talk to us at all. They just set up what they thought would be a good thing. And that was done by S3. S3 said, gravitational waves and neutrinos are the next big thing. We have to put some money into that. And so this was the only call for continuing transnational access, i.e. BHTOM scale things, to continue beyond the ORP timescale. And it was a catastrophe. So the challenge, of course, is that there's lots of communities out there, so ranging from people doing experimental things on Earth in preparation for planetary exploration, all the way up through to future cosmology experiments. And all of these communities were actually trying to survive as communities. Not surprisingly, they've all been, people have devoted their lives to learning how to do X-ray astronomy, or gamma ray astronomy, or planetary exploration, or whatever. And so simply decreeing that this was the only future led to an unfortunate fragmentation and competition inside the existing communities. And the problem with the cost of that is that EC funding is quite small. I mean, the all budget's only 15 million over 4 years, which is compared to the total cost of running astronomy is tiny. It's about 1% on ground-based astronomy, excluding the big facilities like ESO. But nonetheless, this is the only money we have that allows access to anybody with no national or partner constraints. So even in ESO, only about a third of European countries are members of ESO, and the other two-thirds are given in big charity, but they don't have rights to anything. And so this money is very, very important. Now, to try and improve communications, the solar system people have said we should start trying to talk to each other a little bit better, and so that's underway. But that's a future proposal for us to talk to other astronomy-related groups. It's not involving any funding for anything. Got it. So, but what we have to do is have some models for what comes next. What are we going to do? So the first thing that was really important to remember is that EC has changed. They are no longer interested in the idea of continuing what they've done for the last 25 years, which is funding a community to do what it does well, and to act like good Europeans. It seems a bizarre statement to have to make, but it is true that the European Commission is no longer interested in funding European collaboration for basic astronomy. And so where, of course, you have only limited funds hanging on the fringes of other things, and people end up competing with each other rather than collaborating, and that's not helpful. And our experience through both the planetary science and the nuclear astrophysics and so on communities, through optical and radio and into X-rays, is that communities don't merge together. It's just that the sociology and psychology and cultural backgrounds are so different that people have actually very little in common with each other. So the experience of people who might be building a robot to go around the moon is utterly different from people who want to look at use small telescopes to try and find a black hole. And so they have nothing in common. And so what happens is that one builds parallel and federated systems, i.e. you have to duplicate the management basically under a pretend coordination, which does little more than coordinate the reporting. And so that we're not efficient at all, but we have failed to design a better way of doing it, or find better subject groupings. There's some discussion going on as to whether electromagnetic astronomy might be a natural subject, which would mean optical, radio, and add some of the X-ray and high energy astrophysics, and maybe that would be a natural thing that we can present to the Commission, but people haven't yet agreed on that either. And something that's never been considered is whether there's a user-based rather than a facility-based model. At present, the people who apply for the money are the people who own the facilities, and the users are just ignored. One just assumes that the users are the customers of the facilities, and the facilities will look after them. But of course, the priority of a facility manager is to ensure that that person's facility survives, not that that person's users are best treated at the cost of his own or her own staff. So that's an issue. So where are we at then? Well, we all of the astronomy communities that I've just talked about have the same challenges. We don't have a strategic vision of how we should interface with the Commission. And this is partly because the Commission no longer seems to show much interest in user communities. They're only interested in infrastructure communities. And it's partly because we haven't been able to get together and find things in common when there is only a very, very small amount of money on the table. And so people, when they look at a small pot, tend to push their neighbours aside rather than join with them. And so we don't have models for our own future which are either desirable or feasible. We need to do something new. And in particular, we need to think about what this Commission, taking seriously this Commission's phase, which is transnational access sustainable beyond EU funding. And what they mean by the word sustainable is that we are not going to give you anything. You have to manage yourself. Now, in many ways, plastic, you can recycle plastic, but we're talking about telescope time, and we're not going to recycle that. So we need to think very imaginatively about new ways, backup funders, new ways of getting the support that we need to keep our communities operating. And so where are we now? Well, there's no call coming out. There is the latest round of calls for the Commission for Projects is just opened this week. And there is a call in there for new technology development. And there will be a set of responses, competitive responses from the astronomy community, but that's for building big instrumentation related to ES3 scale, the LTI, ELT type things. And there's nothing to continue TNA funding. So in the next call for things that would naturally start when ORP ends, there's nothing. There's no opportunity for us to ask for money. And so we know that when ORP ends, the money ends. It's not any longer an inconvenience where a new contract would appear from somewhere. It's now a fact. And as we know, the most recent call was for multi-messenger astronomy, and that failed. It was the proposal was basically built and coordinated by the astroparticle community, with astronomy being forced to sort of piggyback. But it was terribly disruptive, and there was no planning, and it failed. The various competing proposals that were put in were rejected. Now, it is likely, given that multi-messenger astronomy has already been approved as the highest priority for the Commission, that they will put out the next call with some better defined conditions for multi-messenger astronomy. And so that this community will get another chance to bid for money. That will even further delay an ORP type extension, which would have to then go the following cycle. And so that's all very depressing indeed. And so we are now in the situation where we need to think of much more creative solutions to time domain astronomy, BHTOM, that scale of small international collaborative science that you have all done so brilliantly, is how we're going to keep it operating in another 2 years' time. So I come back to my original statement. More than 25 years ago, when this whole process started, and after a big meeting, big international meeting held in Brussels over 2 days, I was asked to lead a proposal for what became Opticon. And we've had a great 25 years since then. I think things have been achieved, I've enjoyed it. But we've got to the stage where I now couldn't do it. So I don't know what comes next. So I think we need to take the opportunity of this week not only to think about all the amazing stuff that's still going on, but how we're going to keep it going on in 2 years' time. So that rather sort of nice looking back, we've come a long way, we've done wonderful things, it's been a great quarter century, but the next quarter century is not going to look after itself, we have to look after it. And so in between all the wonderful talks and exciting results, let's start talking seriously about new imaginative ways of keeping all your exciting stuff continuing. I'm going to stop there. I'm not going to say thank you because it's a gloomy message, but really, thank you. That's what I have to say.
Thank you, Gerry.
You did a great job. Yeah, okay. Are there questions to Gerry? And we might switch mics. Introduce yourself.
Yes. Thank you, Gerry, for the talk. I have a question. You have mentioned that we urgently need. I'm Paweł Zieliński from Toro. You have mentioned that we urgently need the strategic plan for the astronomical community. As far as I remember, Astronet prepared some astrovision for the next decade. Is it something that we can use for this, or maybe you have some other idea how to prepare this strategic vision and who has to do it?
That's very good. Now it's green. Well done. We need a Lukash to make microphones work. Very perceptive and interesting points there, Paul. You're right. We do, in a sense, have a vision of where we want our astronomy to go. And partly that's in the Astronet vision, and partly it's in all the other roadmaps we have around. I think, frankly, as an astronomical community, it's very, very obvious where we're going to go, right? We've got all these new facilities that are going to be coming on stream. There's all the time domain, the big time domain astronomy things. There's all the high energy physics things. There's all the high energy astrophysics things, the new next generation X-ray satellites. So all these big things that take decades to build are underway, and so we know what's going to come out of that. And we know that some things are just starting to work, like gravitational wave detectors, and they're going to get better and better. And more stuff's going to be discovered. So we know the scientific strategic plan very well. The challenge we have in terms of what I should have made clearer is the strategy that we lack is how to link our scientific ambitions to the funding systems in such a way that not only big money for big new facilities, the SKA or whatever, is made available, but also smaller, longer-term funding to keep what we have that underpins that. Because it's too easy for the people doing strategic things to forget that what we have is a pyramid structure, and we keep adding blocks at the top, the ELT, the SKA, whatever, and they're brilliant. But we're not going to make much progress if we do that by taking the entire bottom layer away. The whole pyramid just goes down one, and we haven't gained anything. We just lost all the people at the bottom. So that's what we're missing, is the connection between balance. And that's, Astronet didn't address that at all. Nobody has, I mean, that's left for us as a community to make our initiatives to go and meet the people in Brussels, or to come up with imaginative new ways of using other money. And there is other money available. There are various options that we're all looking at. We can say, hey, that could be used in this way, and so on. So I think that responsibility is left with us at that practical level, rather than the top level. So we can't ask Astronet to solve our problem for us. They've said, it's your problem.
Okay, thanks.
Jan Ratajczak, University of Warsaw. I have a question regarding the European Commission alternative. So we know that the big parties like ESA or ESA are actually set up by the member states, money basically. So is there any way to have an instrument that's actually would be able to finance the things that we are talking about via some kind of a member states parts?
Yeah, there are ways of doing that. They're very, very difficult to establish, and they're the most common form. There are lots of them legally, all the way from intergovernmental treaty organisations like ESA or ESA, which require all the government parliaments to approve a permanent long-term budget. That's very, very hard to set up. Down to the most practical things, which are called ERICs. But again, these are the same things. They're much smaller numbers of partners, but they do require governments to commit long-term to funding. And so governments, we've asked, of course, governments and funding agencies are very happy to do that for facilities, but not for a sub-part of a facilities operation. So, for example, right now, LOFAR is becoming an ERIC. And so we asked, well, could we have a sort of extra bit of LOFAR/TNA as an ERIC? And they said, no, we fund LOFAR, and it's up to LOFAR and its community how they distribute the resources that we are going to give them and how much it's needed. And so LOFAR is a good example. There's lots of countries in it. But again, if you're not a member of LOFAR, you cannot easily have access to that cash to pay you to go and do something, or to operate your little local telescope in complementarity with LOFAR. So that link is missing. So the long-term treaty things are just really hard to set up because governments have to vote for them, and governments, and in a place as big as Europe, there's a government changing every week, and so it's really hard to do those things.
Yes, hi, this is Ilse Vermeulen from Jive. We are in ERIC, so I just wanted to comment. One of the structures that the problems we face is exactly what you say. The funding has to come from a national level. There's nations that are member states of the ERIC. And at national level, we have to compete with tons of other areas, tons of other funding that has to go out. So it's not a very straightforward model. And in fact, in the Netherlands, they are considering to change the whole scientific funding scheme. So for the next 1 to 2 years, we're still okay. But after that, it remains to be seen how viable an ERIC will be in the longer term. And this also brings me to my own question. I was wondering 2 things. First of all, what always bothers me a lot is that the European Commission seems to completely disconnect from the active science field. Whereas in the US, you see big results lead immediately to increased funding and more support for a field. I mean, the Event Horizon Telescope, we saw a big result in 2019. Within Europe, the funding was basically invisible. After that, in the US, they're writing $80 million proposals for it. Is there any way that you can see that we can overcome that bridge? It puzzles me to no end.
That's you raised a lot of lovely points there. First, thank you for your summary about Eric's work, which is much better than I did, and very clear. The interesting complementarity of the US system, where you can have big projects, or if you get time on a big facility, JWST or something, they give you money, real money, to hire a postdoc or a student to work on it. And the European system is fundamental, and it's unfortunately it's written into treaty law. So the first thing we did when Opticom was founded, Opticom task number 1, was to actually set up a little working group to write a proposal to the European Commission to duplicate the US funding system and provide funds that would come across all subjects. And a big study was done. It was led by Piero Benvenuti, who many of you will know, very prominent, successful. And it was all looked at by the lawyers and finance people and so on. A proper proposal went into the Commission for something that would become Commission law. Instantly rejected. Said no. It's not possible because the treaty structures disconnect science from ordinary funding, or they provide it in a specific way. So, for example, ESA has a science program that is mandatory. If you are a member country in ESA, I've forgotten the number, something like 20% of your money has to go to the science program. But in that treaty, it specifically says none of that will go to any individuals. It goes only to infrastructure, industry to build equipment. And ESA is not allowed to give you money if they give you telescope time. It's forbidden by law. And so the Commission, after Piero's report, went in and said, this is just far too complicated to ever change. There's too many treaties here. So we're not going to follow the US system. And on balance, I think that's probably been better for Europe, because the US system is so dependent on whims and which particular, not necessarily mainstream politician currently holds the balance of power and which particular votes and so on. So we're more stable, and that was what led, I think, to the US decadal survey saying, gosh, we wish we were more like Europe. And so it's a dangerous thing to say we wish we'd be more like America, so you've got to be careful what you wish for there. But no, we don't have a system like that, and we've tried very hard to get it, and we're not going to get one. So supranational funding can be got, so far as we know, either from philanthropy, and there's not much of that in Europe, or from the EC. And that's what the EC is for. We just have to remind them somehow.
Okay. There is a hand raised by the director of JIVE, Aga.
Hi, can you hear me? I'm really sorry that I cannot be in person with you. Good afternoon. I have just very short comment because I can imagine that we're already off the schedule. First of all, indeed, I mean, for great that Ilse is there and she can already, make statement for the ERICs. And of course, I mean, LOFAR as being in the future an ERIC, they can provide the TNA as we provide. So the only point is that, yeah, indeed, we need the calls from the EC for the TNA. And I just wanted to mention that last week there was, under the Spanish presidency of the European Council, they have organized a meeting in Tenerife for the global dimension and sustainability of research infrastructures. And RadioNet was very well represented there. And there was also Nigel from Europlanet. And we have been, we were not the only ones that mentioned how successful TNA was. And I think that EC representatives, they really got this point that where the TNA calls are really required, and we needed to sustain, I mean, even some of the ERICs, right? Because I mean, many ERICs, not only JIFE ERIC is providing the TNA access. There are other ERICs that also use TNA extensively. And as also Gerry mentioned, I mean, many of the infrastructure that now, one of the model is to become an ERIC, like LOFAR is becoming an ERIC, and also Cherenkov Telescope Array. They also submitted papers to become an ERIC, but I mean, not for all infrastructure, this is the best solution. As for example, the Nigel studies from Europlanet show that for them, not necessarily the ERIC is the best scenario. So it's really depending on the infrastructure and how do you organize the community. Yeah, this is what I wanted to add to the discussion.
Thanks, Olga, for the update. That just strengthens, I think, what we've been saying all along, that we need to somehow persuade the Commission to live up to its promise and be European.
Okay, I think we need to stop, but that's great that Gerry gave us this, well, despite being quite gloomy in conclusions, I hope it triggered some discussions which will continue throughout the week. Thank you, Gerry. Let's move on to talk of Fabian. Sorry. Just press. It won't work here. Just a second, give me a moment. I need to press, I need to find the green button. Yeah? There you go. Screen, all yours.
Thanks a lot for the invitation. So I'm not part of Opticon or RadioNet. I'm coming from the high energy community, but we are struggling with the same issues. So I'm running the transient and time domain program of the HES very high energy gamma ray instrument. And in that context, I started to develop this platform, which is called Astro-COLIBRI, to make our life easier. And that has been developed over the last years. And the aim of this presentation is to see if this is something that is interesting for you and how we can connect to the tools that you are using, like BHTOM and others. I'm coming back to the funding issue. So this has been started basically by a tiny bit of funding from the AHEAD project. So we got a postdoc funded through that, and that started the whole issue. So on a positive note, even small amount of funding can make an impact in the end. But of course, also AHEAD stops, if I remember correctly, next year. So in the same situation, running out of community funding. So just as a very top level introduction, what our idea was and where we came from. So we have all these various kinds of transient sources sending all kinds of messengers, photons, gravitational waves, neutrinos. We have this fleet of monitoring observatories in space, on ground, monitoring the sky basically 24/7, sending then alerts on these detections of these various messengers and therefore various sources. These alerts go through various channels and brokers. There's been growing historically, so supernovae are announced to the TNS, GRBs, which is basically the same thing but detected in X-rays, go through the GCN. So there are various of these systems. And these are then used to trigger follow-up observations, learning more about the physics behind and the phenomena at hand. So this works all very nicely, but of course, I already mentioned that there are various of these broker systems, various of these distribution channels. It's harder to keep track of what's actually going on, if this one GRB is related to the supernova, if they are announced on totally different systems. And of course, most of these systems rightfully so, are meant for machines to be reacted to. So we want to have these follow-up observations triggered by machines, basically. So we want to have to remove the human in the loop, which creates delays. We want to be as fast as possible. But of course, then you have all this information being transmitted in XML files or emails and whatnot, and it's hard to keep track. For us as a scientist, I'm curious of what's going on, following which of these sources are the most promising ones, to keep track of actually what's going on a day-to-day basis. And of course, this automatic triggering of follow-up observations is only part of the story. I guess everybody in the room knows that most of the interesting follow-up observations are triggered manually. I require discussions within your colleagues if a certain proposal will be triggered, if it's worthwhile doing that, or rather this, or wait for the next event next week. So what we tried to invent there as a top layer, helping people doing these follow-up observations and keeping track of the transient sky, is a central platform which listens to all of these various brokers, combines all that information in a single place, provides an easy-to-use interface, so you can actually easily use that. Don't have to read your emails all the time. You get the information with modern technology pushed to your smartphone, for example. And then, of course, we shouldn't forget about all these expert systems that have been developed over the last decades by each instrument, by each community, providing detailed information about their science case, their sources, and things like that. And we try to have all these links diving directly into these expert systems to learn more about the source at hand. So if you get an alert, you get immediately the context, you can immediately dive into the detailed system if you need more information than what we can provide in this first top-level interface. And so that's the idea. We have implemented all of that. I don't go into the technical details with the databases and all this listening to all these various systems. We have these interfaces. They run on the web. That's the main thing I'll show today because it's easier to illustrate on a screen. But exactly the same information you also get on your smartphone. So we leverage the new technologies and try to modernize how we do follow-up observations and transient astrophysics, and I'll come back to that at the very end. So I'll run you through the main features of this website, so you get an idea if this might be useful for you. And then, of course, the main aim of the presentation is to get your feedback, what you might see, what is missing, what you would need on a daily basis, so we can discuss throughout the week how to get that done. So if you open the website astro-colibri.com, you get this overview. The first thing you see is a sky map and a list of events. The type of events is coded in the color, and the detecting observatory is coded in the marker style. Then you can select your favorite event on the sky map or on this list that you see at the left side there to learn more about that. You have a list of all these observatories we are using or we are listening to, all these types of events. You have also a timeline, so you don't only see the spatial distribution of events, also the time distribution. So, for example, if you would see a GRB and a supernova at the same position in the sky, but they're like 2 months apart, and maybe they are not linked, you can all select this time range by just clicking on these date buttons at the end, for example, so you can expand and reduce that if it's too much information. These buttons over there is the legend, but you can also use them to filter out the events you're interested in or not. And then for each of the selected events, you get a part of the screen, all the detailed information, where, when, by whom it was detected, what are the properties of the event, the parameters, etc. This is a view that is also meant for amateur astronomers, so there's a small text describing the event. Maybe not very useful for you, but so there's a science mode button that you can click to get rid of this introductory text and get more detailed information that you can also scroll. For example, for this Ice Cube event that is shown here, you get the Ice Cube event display if you know how to read that. And then at the very bottom there, you get this long list of links, and that's what I mentioned earlier on. So there you can get these direct links to these external expert platforms. For example, in this context here, if you get an alert from Gaia that is then classified, so it shows up in our platform, and then you can dive directly into the detailed information on the Gaia Alerts platform. You don't have to remember the name of the alert because we always have these direct links. So to all of these platforms, you get exactly the information for the event at hand. Other things you can do is you can do cone searches, so in the spatial environment of a selected source. That's most useful for the high energy things. So for example, if you have a high energy neutrino, you want to see if there's a flaring blazar in the arrow region, for example, so you can do that. You can also use this box, by the way, to search for sources. So if you don't remember the name of your GRB or your supernova, you can start typing there. There's an auto-completion, then you can search for it, which is quite convenient. Then you can customize the whole thing at the top there. The most important one is certainly the definition of a follow-up observatory. So we have a list of predefined observatories there. Again, they call if your observatory that you use on a daily basis is missing there, just give us the parameters and we can add that. You can also define your own. So either based on the GPS location of your phone or your laptop, or you just enter the coordinates on Earth there. That's of course very helpful for amateur astronomers. They can put in their coordinates of their backyard. But of course, again, if there are a few observatories missing, just let us know, or you can store them. Also, you can save them. If you create an account, you can save them for later use. And this definition of the follow-up observatory drives then the calculation of an observability figure that shows you the altitude of the given transient or of the given source the next 24 hours or the next month, overlaid with the moon and the sun and the darkness and all these things. You can also define an altitude limit, so you get exactly the observability window written on the plot, and you can use that to communicate with your on-site crew if you want to. Recent news, so that's online only since last week. We finally added a share button on the screen where you can now create a deep link to a selected event. So if you want to discuss with colleagues, I found this event, or I got a notification and I want to discuss with my colleagues this event, which is on Astro-COLIBRI. You can create a link there, send this to him, and your colleague opens the screen exactly at the same event, maybe with his favorite follow-up observatory are selected. One word which is very current at the moment is gravitational waves. So of course we also include gravitational waves. We show these contours, localization contours. We show all the parameters. There's also a schedule button where we collaborate with another team which provides the tiled by observation planning platform. So we set up an API on the cloud where you can then push that button and get a list of observation tiles on the sky, so an observation plan depending on the parameters of your telescope, how to cover that uncertainty region most optimal, including all the 3D correlations with the galaxy catalog, etc., etc. So that's quite convenient. You can use that now with a click of a button either on the web and as I said, also on your smartphone. Talking about the smartphones, so there are apps on Android and iOS with exactly the same features and the same functionality, plus an added value. So there's a menu in the top right corner there. You can select notifications. So if you're interested in GRBs or interested in supernovae or high energy neutrinos, you can select these and you get them in real time. As soon as there's a new detection, you get a small notification on your phone, and you dive into the app and see if it's visible for your favorite observatory and then trigger follow-ups. That brings me to the end of this talk. So we have built this Astro-COLIBRI platform, providing easy access to most of the transient detections. One of the things that we are currently doing to keep the flood of optical transient under control, we only add them once they are classified. So once they're showing up on the transient name server as a classified type of transient. We know that there's increasing demand to also add the events right after their detection, which of course would improve and increase the number of follow-up observations, so that would improve the number of classifications. So there's a science gain there. For us, it just means an order of magnitude more events and alerts. So we have to work on the filtering to get them down selected more easily with more fine-grained filters and more fine-grained notifications. We are currently working on that, so that should be coming up very soon. And of course, your feedback is very helpful for that. So I mentioned these interfaces. The main website where you can also find links to these apps and all that is astro-colibri.science. That's also the access to our API. So all the background access to our databases, and that can be done by APIs. So if you have your own system, you can plug that in. There's a documentation on the same website. There are a few papers if you want to read more, and I'll leave you with this final page and look forward to your feedback. Thanks a lot.
Thank you very much. So yes, you need to switch that along. Yeah. Just wait.
Hi, thank you for this amazing talk. I was wondering, I was wondering because with what you said in the end, it was not clear to me. So the targets that you have on are only the ones that are classified, or not all of them, right? Not all of them that you get from the TNS or other I forgot the word for it. Sorry. Yeah.
Exactly. I mean, at the moment, we only add optical detections once they're classified by somebody and have been submitted to the transient name server. Okay. But that's a clear thing we are working on.
Yeah, I'm sorry, I think it's that.
Yeah, I guess it's me now. So that's something that has been coming back also from the amateur astronomer community, which is heavily using the platform. They would want to know where they can make an impact and start observing for a bright new transient and help classifying this event. And I think that help is very welcome. So that's something that's coming up in the next weeks, maybe a month or two or so.
Oh, okay, great. Yeah. Can I ask another one? So when you plotted when you showed the part when you have gravitational wave detections, so do you have in that case, like there are a lot of alerts there, but they are the points that you have, the alerts that you have, are they time dependent? So are they, the ones like the stars and the circles that you have plotted? did they happen after the trigger, the gravitational wave alert was there, or it is you plot all of them since the beginning of the Astro-COLIBRI?
No, so in the general view, so the default time range that we select is 2 weeks.
Okay.
So that you see at the top in the time range view, right there, there's this band. But then, of course, you can change, right, easily. You just change the starting date to the detection time of the gravitational wave.
Yeah.
And then you see everything that comes afterwards.
Okay, I think it would be extremely useful to have this option, right, to have gravitational wave, and then you start plotting all of the triggers, not trigger, the TN, all the transients reported. It would extremely help follow-up observations for this.
We could make it more automatic, probably.
Yeah.
A good one.
But that would be great. Thank you. Any more questions?
Hi, this is Josh Hamsch from Belgium. I'm an amateur astronomer. I mean, it's a very interesting app, but it was, of course, much too short time to explain everything. Maybe I missed it in the beginning. Do you also have targets like cataclysmic variables?
Yes. Again, as soon as they're classified in the TNS, they will be added there, and you get a notification for them. So they're classified under optical transient, just general, because they're not supernovae. So for the moment, our filtering is very coarse. So we have everything that is a supernova and everything else in the optical domain. But again, this filtering will be much more fine-grained in the very near future.
Okay, thank you.
So kind of to follow on this, I was wondering, so once you have your target, even classified like CV or supernova, then, so where is the room for telescopes, small telescopes like us? Can we take targets from your list and find which ones are of interest? Or maybe we should, what we've started discussing a long time ago already, can we kind of connect from your system, which says these targets are of interest for follow-up now, and then they fly to BHTOM, and then they're being observed. What do you think about that?
Exactly. I mean, our platform is meant to trigger follow-up observations. What we get as feedback and what is missing for most people, mainly also amateur astronomers, that they say, okay, then I observe, but then I do what with my data? Right? And we don't have the manpower nor the expertise to provide a platform where people could upload their FITS files and we produce the light curves and things like that. And also that's not the aim of the platform. They're much more expert systems like yours, right? So therefore the synergies come into play where we need to interconnect these platforms much better. For the moment, we simply provide the link to the AAVSO. Say, if you observe, upload your data there. But we should talk much more about how to integrate this.
Sure. Yeah.
It's a first such step. We have a recent collaboration with the Unistellar network, and I guess Tom is going to talk about that later this afternoon.
Great. Yes. So we combine both amateur astronomers and professionals and so on. So I think that would be kind of natural to join forces. Excellent. Any more questions to Fabian? Who funds you? Who gives you money, and how many people do you have in your team?
Yeah, I mean, that's what I mentioned. So the main idea started 3 or 4 years ago, and we got a 2-year postdoc funded by the AHEAD project. That ran out end of last year, and now we have a project from the French ANR, National Funding Agency, funding 2 times 2 years of a postdoc. But that's it.
Okay, thank you. I don't see any more comments, so thank you, Fabian. And let's move on to our next speaker. We are perfectly on time. I love it. And I have to stop sharing and then the floor to Stephen Potter from South Africa. Observatory. Steve, can you start sharing your screen and I'll move it to the...
Okay, I'll do that now. Okay. I'm good to go when you are.
Right, we see you well, and the screen is yours.
Great, thanks very much, Lukasz. So first of all, sorry I can't be there in person, but thanks very much for giving me this opportunity to speak to you. So my name's Steve Potter. I'm from the South African Astronomical Observatory. And the SAAO is part of the National Research Foundation of South Africa. So the SAAO is a national facility, and we fall under the Department of Science and Innovation of South Africa. So I'd like to talk to you about a program we started at the observatory about 4 years ago called the Intelligent Observatory. But before I do that, let me just give credit to the names on the screen there. Hopefully you can see my mouse on your screen as well. So just give credit to the rest of the core team. This is a kind of 50-50 split between astronomers and software developers, I guess, and one project manager. So before I tell you about the Intelligent Observatory, then let me just remind you about the SAAO. So the image below is of the observatory base in Sutherland, and we have close on to, well, I think we have more than 27 telescopes there at the moment. On the far right, you can see over there is the Southern African Large Telescope. And then we have 4 other telescopes, which are kind of our core workhorse South African telescopes. There's a 1.9 meter there, and then 2 1-meter telescopes and a 60 centimeter telescope. But we also host a load of other international telescopes as well. So let me just point out a couple. So there's 2 Polish telescopes there. This is the Solaris telescopes. There's 3 1-meter telescopes over there from the Las Cumbres organization observatory. There's a Japanese telescope, a German telescope, and a Korean telescope. But even though this image was taken perhaps 2 years ago, it's already out of date. In the background there's now another telescope in collaboration with Japan, a 1.8 meter infrared telescope. And somewhere on that patch there's now a US NASA telescope, part of the Atlas network, looking for near-Earth objects. Okay, so what's the Intelligent Observatory? So let me tell you what the why is. I'm going to tell you what the why and the what is in this talk, but I don't have time to tell you how we did everything. So let me just tell you why the Intelligent Observatory. And ultimately, because we're a national facility, we're here to better serve the community and users. And that's not just a national community, but it's the international community as well. And this program is, what we want to do is to enable our community of users to submit proposals at any time, and not just limited to the old traditional way of semester applications. We want to be able to allow our users to do science on any time scale, rather than limited to the old-fashioned way of, 1 week observation blocks during a semester. We want to be able to allow our users to continue observing in Sutherland, but not only that, give them the opportunity to observe from remote station in Cape Town, or perhaps even anywhere in the world. And so thereby allow our users to either observe manually, maybe queue schedule or service observing. And we also want to be able to our telescopes to be able to respond to alerts or any other type of computer generated requests. And effectively, we as the SAAO, in doing all this, we want to be able to enhance our national and international partnerships. So that's why, and what the Intelligent Observatory is basically, we're aiming towards, you can see we have a lot of telescopes in Sutherland, but we want to be able to better coordinate science across all of these telescopes in the so-called era of multi-messenger astronomy, and basically advance SAAO into the so-called 4th Industrial Revolution by building upon technologies such as automation and intelligent algorithms. So that was our objective. We started about this 4 years ago. And So we decided at the beginning, we just decided to focus on our three kind of workhorse telescopes, and there's three images of the three telescopes here. Just to give you an idea, the one on the right is a 75-year-old telescope. It's a 1.9 meter telescope. The telescope on the left is about a 55-year-old telescope. That's a 1 meter. And the telescope in the middle is a newer 1 meter telescope. It's about 10 years old. And between these three instruments, they have a variety of instruments capable of spectroscopy, polarimetry, and imaging, including high-speed imaging. So 4 years ago, we embarked on a campaign to upgrade these telescopes. And as of about the end of last year, beginning of this year, all three of these telescopes are now fully remotable, controllable. So including this 75-year-old telescope, it can now be operated completely remotely. And that's not, here I'm not just talking about point and shoot, but complete power management of the dome and the shutters and the mirror covers and the telescope, and the instrument can be completely controlled from anywhere in the world. And so this is an image of, well, it's almost an image taken for our auditors, I guess, to prove that we achieved remote operations. So this is an astronomer based in the UK using one of our telescopes. And this gives you an idea of what you need to be able to remote control one of our telescopes. You need enough desktop space to run the telescope GUI, the instrument GUI, a video feed with audio, and an interface to show the weather conditions as well. But in Cape Town, we also built kind of our flagship remote control room. So in this room, I should remind you that the Southern Observatory is about 350 kilometers away from my headquarters in Cape Town. So in Cape Town, we built a kind of flagship remote control room, which supports 3 remote control workstations. So we can operate 3 telescopes from this remote control station. And just for the fun of it as well, on the ceiling, we project a live view image of the sky. So if you want to know what the current cloud conditions are in Sutherland, where you're remotely observing in Cape Town, you just need to look up at the ceiling and you'll get a live feed of the night sky. So this is a complete overkill for a remote control station, but yeah, it was great to have. So we achieved remote capabilities for all our 3 telescopes. So what was the next step? The next step was to go for full automation. So we chose the newest telescope, the 1 meter telescope, to do that. And we've now achieved that. So this telescope is now fully automated. It's capable of spectroscopy and imaging with a full set of filters. And in order to do that, we had to write a complete scripting system so that the telescope would just follow a set of scripted instructions, and also incorporate a weather service as well, so it knows when to open and close, etc. But on top of that, we also developed, well, we didn't develop, but we adopted the observatory control system from the Las Cumbres Observatory. So we were very fortunate that a couple of years ago, the Las Cumbres Observatory open sourced their observatory control system. So this software provides the high-level interface for managing observers, their proposals, and their observing blocks. This is the web interface through which they submit their observations in the queue to be observed on our 1 meter telescope. So this also produces the nightly queue, depending on priorities and availability in the sky and all that sort of thing. So we were very fortuitous and very thankful to Las Cumbres Observatory for making this open source, and we adapted it for our 1 meter telescope. But a key aspect as well to this observatory control system is they also provide an API such that you could programmatically submit observing requests to be inserted into the queue. And that was an important ingredient for the Intelligent Observatory program. But it's not only that, we wanted to go almost end to end. So not only do we want to automatically submit observation blocks, we wanted to automatically reduce data as well. So we've achieved that for this telescope. So this is an example of a full wavelength and flux calibrated spectrum. I think this is of an AGN, I think. And so now we've automated this. So within less than 30 seconds, you will get through a web interface, if you like, you can get a fully flux calibrated, wavelength calibrated spectrum from this telescope. And as I said just a moment ago, the OCS or LCO also provide an API so that you can programmatically submit proposals. And we're already doing that. We're scanning for gamma ray bursts and that sort of thing. But one thing a couple of things I like to highlight here, and one is we now host in this blank area of ground here. There's now a new telescope here. It's the part of the NASA Atlas network of telescopes around the world that are scanning the skies for near-Earth objects. And we've now scripted this such that we're scanning the alerts that comes from this Atlas world network, actually, not just the one based in Sutherland. And as soon as an alert comes in, it programmatically submits a script, submits an observation request to the OCS of our 1 meter telescope and gets put into the queue straight away. And this has proved very fruitful because since January last year, this telescope, we've already triggered on 145 new discoveries from Atlas, 88 of which were automatically observed with this telescope. And of those 88, 71 of them have now formally been entered into the MPEC, was that stand for? The Minor Planet, I can't remember what EC stands for, but the official Minor Planets consortium within the IAU. And here's a couple examples of near-Earth object discoveries. You can see there's an obvious one there in this animation, and there's another one. It's quite faint. It's moving down the screen there. So this is one of the powerful things of being able to automate a telescope to make it fully functional and available for timely events like this, for example. This is another example. This is actually from September last year already. So you may remember the NASA's DART mission, where they basically fired a projectile at the moonlet Dimorphos in September last year, and we were able to schedule the Lasady telescope quite nicely so it actually captured the impact and the corresponding ejection of matter from the asteroid, from the moonlet. But in addition to that, so that's kind of demonstrating how we can now use the telescope to rapidly react to follow-up events, but we can also follow Gaia alert events. So this is a micro-lensing event, Gaia micro-lensing event earlier this year. You can see how we nicely captured the multiple caustic crossings of this. I think it was a binary system was the lensing system in this case. So this telescope can now do time series on large scales. At the other end, the telescope is also capable of high speed imaging and over a continuous time base as well. So this is a long train of high speed observations over, I think this is more than 5 hours. And this is of a new system that was discovered last year. It's one of these so-called new white dwarf pulsing systems. So you can see these sharp peaks of the short period, I think it's just about 3 or 4 minute long pulses from this white dwarf pulsar system. But then, of course, what we're able to do in Sutherland is then coordinate follow-up observations of important targets like this throughout all our facilities in Sutherland with follow-up high-speed photopolarimetry, and high-speed spectroscopy with SALT. Of course, in South Africa, we also have the Meerkat radio telescope, and they also discovered this source to show a very short radio pulse on this white dwarf spin period as well. And these observations are actually combined with X-ray observations and other optical observations around the world, and we got 2 papers out earlier this year on this system. And of course, it's not all just science, it's all a bit of fun as well. So earlier this year, we submitted one of our kind of commissioning images of automatic observations to Oxford Instruments. They produced these Andor cameras, and we won the competition for that event for these cameras. So finally, moving ahead, our next stage is, as I said earlier, we got 3 of our telescopes are now fully under remote control. Now they're under remote control, basically that means they're all under software control. So it's a relatively easy step now to fully automate the next telescope. The next telescope we have our sights on is our older 75-year-old 1.9 meter telescope. And what we've done there is we've just in the last couple of weeks, we've upgraded the instrument package on that telescope so that it can now host more than one instrument at once. So one of the key things about full automation is the ability to, under software control, automation control, flip between more than one instrument. So this is kind of an advert for our workshops that we have in the headquarters in Cape Town, which are fully capable of high precision engineering. And we also have an optics lab. And just last week, we installed on our 1.9 meter telescope in Sutherland, this instrument selector pack. Well, basically, this is a new auto-guider mechanism. This is the back plate of it. And now this back plate can be replaced with an additional instrument. And this is a first light image from a few nights ago. Okay, I think I'm running out of time, so I'll stop there. Thanks for listening.
Yes. Pleasure again. Thanks, Stephen. Questions? Lena.
Hello, it's Milena from Poland, from Warsaw. First of all, congratulations, because I've spent many nights using 1.9 telescope with giraffe spectrograph, and many things went nice and many things went wrong. So I'm really impressed by what you achieved with the instrumentation right now. I have a question regarding to this 1 meter telescope and the very fast photometer that you use. What's the limiting magnitude of the sources you can get with this instrument, and also what's the cadence? The shortest cadence that you can achieve. Thank you.
Cool. Thanks for your comment and your question. Yeah, so it's a 1 meter telescope. So we have an Andor camera on it. Yes, an Andor camera on it. And with long exposures, you can go as deep as the sky allows you, right? So maybe 21.5 magnitude in the V filter. For high speed cadence, we can certainly do sub-seconds, so maybe 500 milliseconds. If you go any faster than that, then you start running into competing with the readout time of the instrument. But we also have another camera on the other 1 meter telescope, which is capable of, I mean, last night I was running at 50 millisecond cadence, and that was with no dead time at all.
Yeah, sorry, just these are CCD's cameras or CMOS?
These are normal CCD cameras, frame transfer cameras.
And then how faint you can go?
Well, on the 1 meter telescope, I should imagine 21.5, 22 with long enough exposures.
But the millisecond exposures.
Milliseconds. Well, then that depends how bright your star is, right, and what signal to noise you want to use.
So the light curve you showed, the flickering light curve, how faint was it?
Okay. Yeah, so that was those were about they were 5-second integrations.
5 seconds.
Each data point there, yeah. But
And
that's
what's
a delta
the-
mag scale there, so I don't know what
Yeah,
the real
okay.
magnitude was.
I see.
But if any of you are aware of the Swift 17, what's the there's an exciting black hole binary event happening at the moment, right? Swift 1727, I think it's called.
Yes.
If you know how bright that one is, we're currently doing 50 millisecond photometry on that source with the 1 meter telescope, and we're getting a good signal on that one.
Josh, what was it?
It's magnitude 13. I am observing it from Chile.
You are as well, okay, 13.
Yeah, we discussed it.
There is something exciting on the sky. Josh is already observing it.
Yeah.
I have a question about the white dwarf pulsar.
Okay.
Is it similar to AR-Scorpii?
Yeah, it's
Yes.
extremely similar.
Yes.
So we just published a Nature Astronomy paper on it a couple of weeks ago. So look out for it. But
Do you
yeah,
have
the whole multi-wavelength characteristics are identical to AR-SCO. Radio pulses, optical pulses, X-ray pulses, and it's also highly polarized as well.
Okay.
Can you share the publication?
Yes, in the chat.
Or it's Slack channel, please.
Okay. It's on the bottom right there as well, if you can see it.
All right.
I'll put it on the chat channel just now.
Thank you. Are there any more questions? Please.
Hi, Stephen. This is Ilse from China. I had a
Hi.
question about the involvement of the Meerkat observations. I assume these were dedicated observations for this target, or were they actually scheduled jointly with all the optical?
Yeah, we applied for DDT time for Meerkat.
And are you planning to involve Meerkat in this time domain as well, or is that a tricky thing?
Yeah, there's a few key programs going with Meerkat. One of them is called the Thundercat program, and well, that's more of a transient program. But for the Meerkat project does have a general open time for applications, so it is open for the kind of time domain astronomy as well.
Thank you.
I should mention that Meerkat is now gradually morphing into SKA moving forward. So yeah, there'll be big developments in there in the next few years.
Okay, I don't see any more questions. Thank you, Stephen, and thank you all the speakers for this very short session. Yes, we can talk. It's time for a coffee break. So we return here in about 45 minutes. 45. The coffee is served outside. Or you can go and have it.
You take coffee from here, but you can go with it wherever you want. You can go there.
Tu, teraz już nas słychać. Dzień dobry, jeszcze masz minutkę. Ale mogę cię już wrzucić. A chcesz, pilota masz?
Mam.
A co, jak ja zabiorę to okienko. Przeszkadza. Też można. Pan ma dzisiaj? Tak, oczywiście. Stawiamy serwer do jutra rana, jakby się zauważył. Okay, welcome after the break. We begin with a review done by Mikolajczyk from Warsaw about BHTOM.
Right. Hello, everybody. So
More enthusiasm.
in my talk,
More caffeine.
in my talk, I will show the developments that we already implemented in BHTOM2, with the emphasis on the processing software, which is called CCDPhot2. Let's begin. I would also like to add that there are some contributors to this work, especially of course Lukasz and Paweł Zieliński, who I cannot see, probably still Ringsby. Yeah, and Akon Lab, which is the company that is supporting our efforts, and I will show something more about as well. So let's start. Try now. Yeah. So let's remind ourselves what is BHTOM. And Paweł just entered the room.
Hello.
I already told that you are contributing to this work. So BHTOM is a black hole TOM toolkit, which is based on TOM software provided by LCO. And the idea and the goal is to provide support for small observatories, large observatories all around the world. And we would like to process feeds files in a homogeneous way, and hopefully be able to also manage target observations, triggering, and so on. And here you can see the web page that you can visit. And there is so right now there is a first version of our pipeline, of our toolkit, but Lukasz tomorrow will tell you more about the upcoming changes. So the idea is to provide to the network of telescopes two kinds of software. First is software that will manage your observations, that will be able to trigger your observations automatically, and will provide you with the list of important targets, interesting targets that you can observe in your observatory. So this is the network of telescopes. And the first problem that we stumbled upon is how to process feeds files in a way that we have a very homogeneous results. Before we developed this, everybody processed images on their own behalf and then uploaded ASCII files. It, of course, produced a lot of artifacts in the light curves. So what we wanted to do is to provide the software, some kind of pipeline that would do it in the same way for every single image that is being uploaded to our network. So after the processing, we of course try to standardize the photometry. So the resulting photometric point is already in the standardized band, and we store the data somewhere in the cloud server. The final result is the light curve, such as light curves presented here, and also there is a possibility to upload spectra, which can also be displayed in the service. So the initial idea was to use open software, not to develop anything new, because it will eat up your time. And there is a lot of routines already established, very well established, that we can use here. So we decided, of course, to use two different kinds of packages. First are Sextractor and Scamp, which will give you astrometry, very good astrometry. And then we kind of had to decide how to do the photometry. The problem is that the best software there is for profile photometry for crowded sterile fields that we would like to extract photometry from is DAOPhot. And DAOPhot is how old? It's very old. It's written in Fortran. You cannot really modify it. You cannot provide any parameters to it. But still, it is very, very fast. So we decided to use it. I will show you something later that we kind of have to stick to it. We also use some open software tools like WCS tools, ESA Eclipse, and IRAF, PyRAF, which everybody probably knows here. And it was 2021, and these tools listed here are the base of the first CCDPhot. What happens inside the pipeline is that you simply upload a FITS image, and then in a series of very simple steps, the pipeline will provide you with the astrometric coordinate grid, and then will perform a series of calculations resulting in photometry. We are providing 3 different types of photometry. First is aperture photometry from sextractor, which isn't exactly very precise. And then we are using this photometry to make a better one with DAOPhot, and with DAOPhot we are making aperture photometry and of course profile photometry, which is kind of a goal for us because in these dense stellar fields you cannot use aperture photometry very well. So the resulting, the result is also a subtracted image in which you can see the quality of the subtraction. And the biggest step, the biggest challenge here was to select the set of stars which would be perfect for PSF estimation. So far we were doing this by hand, examining the images, but we developed a simple yet very nice routine which selects a set of stars and then performs the PSF photometry here. And the last step, we are also performing the precision astrometry with the Gaia catalogs. So far we used Gaia EDR3, but now, of course, after 1 year, we adopted Gaia DR3 catalogs. Yeah, and so this is this one more science product, this astrometric time series, and also the challenge here for us in the future will be that we are not only measuring the flux for one single object, we are measuring the fluxes for all objects in the field of view. So basically, by studying a single star, we are providing time series photometry for all of them. So the byproduct in the future will be the catalog of light curves for all objects visible in the field of view of a given telescope. So if you have a very dense stellar field, there will be thousands and thousands of light curves available for the subsequent variability searches and so on. So here are the number of very nice examples. How does this automatic PSF selection subtraction provides subtracted images? So all of this was done without the need of a human interaction here. So we have these 2 not really dense stellar fields, but if we see how it works in problematic field of views, like this with the nebula, it also works nice. And here we have this Gaia 16AYE, which everybody knows here, probably. This was also done automatically. So 14,000 sources subtracted quite nicely. So after the last 36 months, so since the start of the project and since the start of the development of the whole pipeline, we learned a number of lessons. The first one is never trust users, because they will always upload bad data. So there are some examples when people have 300 errors and write to me what happened. You uploaded data for the wrong object to the wrong site. So you have errors because astrometry does not work there. Second, do not process users' data for them. It will eat up all your time. Basically, lesson I learned. Try logging as much information as you can. Even if you think that some kind of prompt message will not come in handy in the future, it may. So log everything you can. Anything is better than DAVOT. And there's nothing better than DAVOT. So you kind of have to deal with this. It's the most unusable software there is, but it's the only one that's fast enough to give us the results quickly and that we can rely that they are very good. And it's better done than perfect. So it's the lesson that I'm learning right now. Just at one point you have to stop looping over your code. Just say it's finished and hopefully it will work. And what is the second version of CCDPhot and how does it work? So it's basically the same concept. This is the same software, but we added something, changed something, and removed some things. We abandoned the pipeline concept altogether because even though it's very reliable, you cannot make many instances of it at the same time. So it's slow. So we removed all the requirements from users. So far, users had to know what is the target. They had to put it in the feeds header. They had to put all the characteristics of CCD camera, of your telescope. Of course, we would like to know all this information in order to maybe trigger some observations, know which telescopes are better for some things. But actually, it's not required right now. So you can upload your feeds and we will kind of try to guess what's inside. We add new methods for performing astrometry and photometry, removed outdated software, so everything that is not supported anymore is gone, and we are sticking with the proven methods and proven routines. So the second version will only work in Docker environment, and the first version will be the second version, but in the pipeline way, so you can still be able to install it on the standalone computer to use it without Docker environment, but it will probably become obsolete in a few years. So the Docker was split up into 6 instances. The first one is Feeds Manager, and it will deal with everything that was done so far with some kind of dictionary that I will show you in a second. Some of you know this. And this Feeds Manager will fill into the feeds headers all the information that is required, and all the information that isn't required will not be even dealt with. So we will kind of try to guess what is your gain if you don't provided it. If you didn't provide your readout noise for your camera, we will also try to guess it. There's only a finished set of CCD cameras, or even SMOS cameras in the world. So once somebody adds an instrument like this and you have the same, you can use this information. And this process is always on in Docker, so it works in the background, and it's probably only a fraction of a % of the time required for processing one file. So this is what you had to provide us in the beginning. And so this is only for one observatory, I guess it's Chile. And right now we just have the database, and these are all the telescopes. And we can add it, change it. You don't have to interact it at all. Second one is the astrometric pipeline, and we can have as many instances of this as we want. So far we could process 8 files at a time in our server. Now it's 16, but now we can do the 16 astrometric calculations at once. We don't have to use the feeds manager because it's working all the time and doesn't eat up our time. Yeah, so we are using exactly the same software, and also after nothing works, we will use the novaastrometry.net. So far it's implemented in a way that we use the web service, the terminal web service, but in the future we will have our own copy of this
in the BHTOM. With the photometric pipeline, we're of course using DAOPhot, and after a decade, Sextractor was also provided with profile photometry. It's called morphology. Yes, so it also can feed profiles to the galaxies and so on. So it should be very efficient, and we will provide this photometry next to the DAOPhot photometry, not instead of, but next to. Gaia Astronomy is also a Docker working all the time, and it also takes a little bit of time in the whole process. So the last step to provide astrometry grid based on Gaia is also a single Docker, and the result preparation, which may take a lot of time because we can have 20,000 sources in the frame, is also running all the time. And this should be all, but so there is one Docker. Like the IRAF is like this uncle that nobody likes but still invites the birthdays and so on. So we will stop using it, but if so far we'd like to check some things with IRAF. So we just have it. We just have to have it around, but in the future we will disable it and stop using it altogether. What are the new features? We improved the photometry routines, added support for the new Gaia catalog. So right now you can also put the whole nights. You don't have to upload 50 feeds files. You can upload TART package and it will be dealt with. I added the support for non-sider targets, so for like small bodies of the solar system may also be calculated. So this PSFX is a big step. We removed the IRAF from the whole pipeline, from the whole Dockers, and wrapped DAOPhot in Python. So instead of giving DAOPhot these ASCII files to say what it has to do, you can do it with Python. And the last one is crucial here, because we would like to provide quality checks for each photometric point generated by the pipeline, by the Docker. It's easy in some cases, like the moon was very close to our star, so we can put some flag giving you notice that your measurement may be a little bit off. But in some cases, I noticed that mostly amateur observers do not know how to properly calibrate FITS images. And it can be checked in some cases. You can check the quality of the flat fielding by checking the vignetting and so on, and by calculating the standard deviation of the background and so on and so on. So it can also be provided as a parameter to the photometric point, which in the subsequent analysis will give you notice that you can remove this if it doesn't work. So these are the statistics from the March 2021. As you can see, we have a steady increase in number of process files. And in some months, we have a lot of errors, which were mostly generated by testing and by sending 500 files to the wrong target. And in time, we should be able to decrease the percentage of errors down to 0.1%. Right now, it's about 1%. So about 115,000 FITS files were processed so far. We have over 200 active users. We are approaching 100 instruments. Observations are both in infrared and in optical. We implemented automatic processing for REM telescope observations, and also we should be able to implement, now that I'm talking to you, LCO processing in the foreseeable future. And the big change is also that right now we calibrate, we standardize all the photometric points, not to like some APAS, GIFAS service. All of them are standardized to Gaia synthetic photometry. which gives much better quality, much nicer curves, much lower errors. There are still a lot of things to be done. First, what we already prepared is a better feedback for users. So this was a constant question from Staszek here as well, that we are not informing what happens when you upload your feeds file. It's just sent to photometry, which doesn't give you anything. Right now we will tell you it's performing photometry, it's preparing results, it's in astrometry, there is an error, and which kind of error there is. So that should work. In the future, we would like to store all the feeds data. The standardized, after the first docker, we would like to store for a short period of time probably, but maybe in the future, if we have to correct something for the scientific paper, there will be a possibility to do that. Also, the star subtracted images, like I showed you already, as examples, we can do the PNG out of it and show the user how it looks. So you can basically tell if there was something wrong with the whole process, even though there is no error. So far we implemented, Lukasz implemented a micro-lensing model to the light curves. We could do the same with the Fourier analysis. If you have a interest, periodic star of your interest, you can basically click and check what the spectrum, Fourier spectrum looks like. The next science products will be the time series for all the objects in the field of view. And we should be adding new facilities next month and years. We have 163 telescopes in our list, from which we're a little bit after half. And I think we saw a map somewhere of all the small telescopes in the world, which probably are in the hundreds. And now it's many thanks to the best observers, not in no particular order. These are the people who provide us with the most number of feeds files. It generated a lot of problems, but these problems allowed us to understand which steps we have to undertake to avoid them in the future. So many thanks. And thanks to collaborators, to Paweł, to Uliana, who provided the new dictionaries for the facilities, to Lukasz, to Paweł, and also to our team from Account Lab, who developed the whole server structure and so on. So these are the contact informations, and if you have any questions, please ask them up.
Thank you. There you go. Questions to Przemek.
Staszek J, Jagiellonian University. A technical question. You said that if I put already CCD parameters, what happens if I move this CCD at the same side from one telescope to another one? So parameters of the CCD are the same, only the field of view is different.
Yeah. Just let us know. We will change the longitude, longitude. So.
Yeah, this is the same. Only the field of view of the telescope is different.
So you put you put the camera to the different telescope.
Yeah.
Nothing. You don't have to do anything. We will know it.
Okay, I checked tonight.
No, don't check it, Staszek, please. Let me have a break.
You should crash test it. Yes.
I kind of was expecting that.
Michał Żymo, University of Żonagura. I have a question about the NOVA astrometry that you saw.
Yes.
You are using it as a blind solver for the images, or because you say there are sometimes problems if users provide a wrong object name, and maybe it's better to place on the coordinates.
Yes, exactly.
Not on the.
Yeah, that's what we are doing already. But the astrometry works. We are using exactly the same routines as the NOVA astrometry. But if you use the NOVA astrometry, you have a huge question to the server. It can be anywhere in the sky, right? So it takes time to solve the problem. But in our routines, we point where it may be in the sky using the coordinates, so that when it takes 2 seconds, if it doesn't work, then we will ask NOVA astrometry to do the kind of Hail Mary to solve.
Yeah, because now if you upload the data with the wrong object name, you get an error, yeah?
No, right now, no. Right now, we changed it a while ago. When you go to the BHTOM, to the target site, and you upload feeds, as long as it is this field of view, we don't need the target name. The feeds, no, we just change, we take the coordinates from the BHTOM and pass it to our astrometry pipeline.
This is a good
yes.
Okay, and I don't know if you know it, but there is a Docker version of Nova Astrometry.
Yes.
And also PlaneWave provide the new version of the Plate Solve tree.
Yeah.
And it's
very
fast and very good.
Yeah, we still, if you have a problem which takes like 30 minutes, it takes really short time. So we are using our. We would like to be independent. In case it doesn't work, and it happens, it used to happen in around 10% of the time, because somebody observed here, then moved the telescopes a little bit more, and then Nova Astrometry will work. And in the future, we will have our own Docker in our server, so we will be independent on the changes they make and so on.
Yeah. Okay. Thank you.
Hi, this is Ilse from China. Thanks. Very clear talk. I'm finally starting to grasp what this tool is all doing. I had a question about the BHTOM2. It seems every field in astronomy has its own software package that's like 30, 40 years old.
Yes.
And we have to love and hate it, but there's nothing else. What makes it so fast? Is it the fact that it's written in Fortran, or that it was developed for old hardware which has better?
Probably a mixture of many things. First of all, this was developed by an astronomer, so Stetson knew exactly what he was doing. And the mathematics, that's the same, because it is a fitting of Gaussian bivariate to the data with the many things, with the correction table and so on. So you cannot really think of anything better. You could probably use some machine learning techniques, but as long as it's not available, we will use this. This is really fast. Even if you have thousands of sources, it will. And we are iterating the process, so we are using this 3-4 times. And after we arrive at the best solution, we continue. So it will, sometimes it takes half an hour to solve one picture with the output. And but if you use some kind of Python software from GitHub, it will take you days.
Is that because of the memory efficiency, or
it's because of its compiled program, and it is very efficiently written. Of course, it has its limitations as well. You can upload. I think in the base version of BHTOM2, you could use 1K by 1K images, but we modified it a while ago, so you can, I think, upload 8 by 8. But even if we have large images, we don't want to waste too much time. We will cut the field of view. Maximum right now is half a degree by half degree. It will diminish our set of stars that were processed, but the time will go down dramatically.
Okay, Josh and then Rupak.
Hi, Przemyslaw. This is Josh.
Rupak.
Just have a comment. I mean, you mentioned in your presentation that you are no longer will process images of users. So I hope you will continue to process my images as I send them every night to you.
Yeah, hi Josh. For you, I think we will make an exception. But to be honest, I did develop a little script in Python that is downloading the data from Google Drive, and it worked for a while, but then stopped. I don't know if it's a credential thing or anything like that. But yeah, if somebody provides us with such a huge set of data as you do, then we will probably have to stick with it. And thank you for doing that.
Thank you.
This is Rupa. Yeah, I'm here.
Hi, Rupa. Hi.
So I just curious to know what are the extra thing in your now new PSF determination? I mean, what's the difference with the default PSF determination? I mean, the cleaning is very good, so
yeah.
I'm big because of that.
Yeah, in default you can kind of specify which function you are using, and this is basically in, as long as the images are sharp, this should be Gaussian, but DAVPhot will provide you with a huge table of corrections. So it will recalculate the flags around each star with subtracting neighbors and so on. That's why the quality of subtraction is so nice. With PSFX, you can choose from many different functions, and we also give you a nice subtraction. When I tried to determine the quality by looking at the subtracted images, I couldn't say which is better, but when you plot the light curve, DAVPhot is much better. Still much better, but I think that it's not being developed anymore. So in a decade, PSFX or the next iteration of it will surely be better.
So you are using PSFX, which is not a DAVPhot, right? Which is from the extractor.
Yes, it is it only gives you the function, the parameters of the function, and then you use Sextractor. And the new version of Sextractor will generate also the profile photometry using the output from the PSFX.
Thank you. Charles Landis from University of Malta. First of all, thank you for this, again, another wonderful presentation this afternoon. I'm a real fan of BHTOM interface, in fact. I find it very neat, very efficient, very clear. And when you said that the possibility of having more information that is being given to the end user, that is fantastic, because for example, if we receive information about the quality, both of our data, but also of our vignetting, if that information can be passed on to us, we can take action immediately, yeah, for the next set of data.
Yeah, that would be nice, because we are kind of operating blindly. The whole idea is not to interact with it at all, at least from our side. And if you have some kind of feedback, then you can do at least the calibration better. But also the whole the information about the measurement. So far, we are providing you with the standard magnitude with some kind of error, but we can also provide you with instrumental magnitude. We can provide you with easily provide you with the coordinates of comparison stars and so on and so on. I think the only real information that you are getting right now about the standardization process is the PNG picture of the feet that was chosen to standardize your measurement. But we can do so many more things. We probably will do in the future.
Yeah, I'm sure that this will take a lot of time, and that's unreasonable, because it's a quite sophisticated system. And secondly, I don't know at what level it is, but if you can upload videos, tutorials, yeah, and also, for example, ways how we can use the script to upload more efficiently our data, that would be fantastic.
I've seen a reaction from Lukash.
I'm getting a heart attack, because that was a plan like a year ago to do that, and Przemek was supposed to do that.
No, I wasn't.
So that's why I'm coughing. Sorry.
Yeah, I know that this needs a lot of time.
Actually, I was supposed to do that.
Yes, your honor, in my defense, it was Paweł's job to do
It's not
that.
Przemek's fault. I must.
Fine.
Yes.
Well, anyway, this is a great idea, and I'm glad you're saying it again, so that we are more eager to do it
Other
now.
than that, the user feedback, and even troubleshooting, that's fantastic.
In the end, we also should have some kind of GitHub repository for open scripts with proper documentation to how to use them and what could be the problems.
Thank you.
Thank you very much.
Okay, thank you. I'm afraid we need to move on. Siegfried has an interesting question, but I hope we can move it to Slack. The question of Siegfried. I hope he's okay.
Yeah, it's quite technical ultimately. Yeah.
Okay, thank you. Right, so we now have a remote talk from Rachel Street. Rachel, are you with us?
Hello there.
Hello there. I'm just moving the Zoom to the big screen, and this screen is yours, so just start sharing.
Okay, thank you. Hopefully you can see my slides.
Yes, we see it perfectly.
Okay. Excellent. Well, hello everybody, and thank you very much for this opportunity to speak. As we've heard, software can be a great assistance for time domain astrophysics, and I'd like to give you a quick update about some of the tools that our group in LCO have been developing. Of course, everything I'm about to show you is the work of our joint team at LCO, so allow me to first acknowledge my collaborators. Everyone is well aware of the massive data volumes that modern surveys now produce, but many people underestimate the workload involved in running a follow-up program. We have this constant stream of targets coming in, which need to be evaluated in real time and prioritized for follow-up. And while researchers are busy following those targets up, more discoveries are coming in all the time. And that cycle is unrelenting and often demands a rapid response, especially for transient targets. And that's why software to help manage this process is so very valuable. And as a category of software, I tend to refer to it as Target and Operation Managers Systems, or TOM systems, but they're also sometimes called marshals. So TOM systems, such as the Black Hole TOM, have proven extremely effective at managing follow-up programs, but they are a lot of work to build from scratch. So LCO has written this open source software package which provides an out-of-the-box TOM system. And this system provides all the functions you need to run an observing program without having to reinvent the wheel. It includes interfaces to a bunch of other services such as alert brokers, data archives, and telescopes, so that you can make the most of those facilities. But each science program is unique, and I like to say that there is no one ring to rule them all solution. So the TOM toolkit was designed to be really flexible and easily customized so that users can optimize their TOM for their workflow and their science goals. And we have extensive online documentation and user support to help people do that. So the first step in the follow-up process is to gather all available information on targets of interest to your science goals, and that means querying alert brokers and data archives such as the Gaia alert system. These are common user facilities, so rather than have everybody write their own tools to query the same services, the toolkit provides built-in interfaces for the set of commonly used services. The toolkit also provides tools for visualizing data, such as interactive plotting and tabulation routines, as well as search functions so that users can explore the data they have. And of course, having retrieved all that data, each researcher then needs to do their own science and their own analysis in order to identify the most important targets, do data reduction, etc. And everybody has their own data pipeline and their own modeling tools that they prefer to use. So we provide hooks into the TOM toolkit, which allows users to plug in their own algorithms and their own software. But it's also easy to add plugins to query external services, provided those services give us an API. So as an example, you can easily connect a TOM service to a service such as the excellent Astro-COLIBRI platform that we heard about earlier. More and more observatories are now enabling users to submit requests for observations directly, so the toolkit provides interfaces for that purpose. And this can all be automated entirely, so it is possible to have your TOM system run the entire observing program without user intervention, although we do provide browser-based user interfaces if you prefer. And we provide observation planning tools, which are useful for all telescopes generically. Lastly, the TOM systems can serve any size of research team, from a single individual to a large research group. Each member has their own account, and the TOM does recognize users groups, which can be useful to subdivide a larger team. It provides the system administrator with a lot of control over who has access to which data products and which targets, if that's something that is useful for your team. And lastly, having performed follow-up observations, it's becoming increasingly important for observers to share their findings with the community as soon as possible. So we've recently expanded our tools for that purpose, and I'll come back to that shortly. So last year, when I mentioned the TOM toolkit, we had a number of features under development at that time, and I'd now like to give you an update on where the development stands with the new features. So Apache Kafka has become the de facto standard for programmatically sharing information on new discovery alerts. And there are a number of brokers that are now providing a range of Kafka topic streams, such as, for example, the GCN Classic over Kafka system, and also the Rubin Observatory alert brokers. So the Toolkit has now a new plugin called TOM Alert Streams, which allows users to configure their TOM to receive any Kafka stream they prefer from whatever provider you have access to. We've also added a TOM classifications module, thanks to some excellent work by Brendan Mills from UCSB. Several broker services, such as Laser and Fink, provide alert classification information derived from different machine learning implementations. And that gives us the opportunity to compare results from different classifiers, which can either be used to build confidence in our selection of targets of interest, or it can also be used to find anomalies which might reveal new physics. And Brendan developed these interactive plots that allow you to compare classifications at a glance and make that evaluation process easier. With multiple sources of new discoveries, it's becoming increasingly important for observers to subscribe to different multiple alert services. And of course, that means that you can get the same targets that are often identified in different surveys. And it can be important to synthesize data coming from both of them, especially, for example, in multi-wavelength data. So we've added more support for target cross-matching. And the cross-matching is performed whenever new targets are ingested, and they're compared by either the naming sequence or by on-sky coordinates. Excuse me. With the 04 run of the gravitational wave detectors now ongoing and neutrino detectors now providing alerts as well, our team have put in a lot of work to support observers in those fields over the last year. The distinctive feature of these events is that they cover extended regions on the sky, which may include a number of potential targets chosen by the user, such as galaxies, for example. And in order to understand the nature of these events, it's essential to combine the multi-wavelength and multi-messenger data in real time, and the race is on to search that localization region for any counterpart signal. Supporting this kind of wide detection area required some rethinking of the TOMS database structure, so we've introduced support for what we call super events. And here, if the video plays, you can see a TOM system that is configured to use this new plugin. It's retrieved a list of the non-localized events announced via GraceDB. The links are included in the table, which can take the user to visualization of the event's localization as presented by the treasure map system, and also to the corresponding entry in GraceDB itself for easier reference. Now, if we return to the index, we can click through to the TOM's own page for an example event, which gives us an overview of all of the data available for this particular event. The table provides a summary of updates from different observers at different facilities, and you can click on each entry to get the detailed information. On the right-hand side, you can see data harvested from the GraceDB, and the top bar provides a quick reference summary of the current classification probabilities. As we scroll down further, you can see the two candidate tables. This is because within the large localization regions for each detected event, there are a number of potential candidates, usually associated with galaxies, and follow-up teams conduct observation of these targets in response to each alert, searching for signs of optical counterparts. So once a target has been observed, it can either be eliminated as a candidate or remains on the active list, where the TOM can then request further observations. So with lots of teams responding to the same alerts and all of them trying to use the same national level telescope facilities, a key concern has been how to coordinate between research teams to make sure that we respond to new discoveries efficiently, rather than everybody rushing after the same candidate and neglecting others. So a key area of development recently has been in tools that enable researchers to rapidly share information from follow-up programs back upstream to other observers. Now, different teams are, of course, using their own software and different packages. So to share information directly between each team with every other team is complex and probably means a lot of different interfaces. Instead, it's much easier to build a common platform for data sharing. One of the new data sharing services that has been developed recently is Hermes, which we developed as a collaboration between LCO and the CIMA organization. The Hermes service builds on Hopscotch, which is a scalable Kafka-based stream, and it offers a web-based user interface, which is designed to be flexible so that users can share everything that they have learned about an alert. That includes uploading different data products, such as tables of photometry, and the platform can also submit the data automatically to other sharing platforms, such as the Transient name service. This platform provides both an interactive web interface and a programmable API, so you can share information to Hermes direct from a TOM system. So here's a short demo of the Hermes user interface. There are different Kafka topics used to select thread of messages relating to different topics, such as GCN circulars or different science subjects, and the filter allows you to review the messages of topics that interest you. Now, suppose you have some observations to contribute. You can fill out this submission form in the browser, indicating which topic to send the message to. And the form is designed to be very flexible, so you only need to fill out those forms which are relevant to your message. But it does perform validation throughout, such as checking whether each field matches criteria necessary for the message to be sent to other services. You can add one or more targets and indicate whether or not this is a new discovery. And all of this is editable manually if the user prefers. But you can also imagine if you have a lot of targets, it's convenient to upload the data from a CSV file, as shown here. And it gives you the opportunity to upload either individual observations or loading a light curve as a CSV table. And again, validation is performed in the browser on each field. You can add data elements as key value pairs as appropriate, and you can also add free-form message text in the box. The message text accepts markup, which allows you to reference selected measurements in the data table, which then get populated automatically. And the form has built-in help pages for anybody unfamiliar with this syntax. But this can be done direct from a TOM system, so let's see how this data sharing works in practice. Here's a TOM system run by Team 1, showing the data they have on a particular target. As you can see, they've got some photometry and spectroscopy. Now, this is a different TOM run by Team 2, and you can see that they don't yet have data on this object. As Team 1 decides they are happy to share their data on this object, and they select all of the data points of the target from this table, and they send it to the Kafka team topic at Hermes. If we go back to Hermes, we can see that post from Team 1, and we can see the data that they shared. So now, if we return to the TOM of the second team, in order to receive updates from other observers, this team have subscribed to that same Kafka topic in Hermes, so they've received messages and the TOM then ingests the associated data automatically. So if we now reload that photometry page, we can see that the data from Team 1 has arrived. Since I know that everybody here is interested in a range of astrophysics, one thing I wanted to emphasize is that Hermes is intended to support all of astrophysics, not just multi-messenger astrophysics. And to that end, we've made it easy to add new topics for different communities. For instance, we're working with the Solar System group from Rubin to support moving object science. And in fact, one of our software engineers did his PhD in that subject. And we recently added a topic for microlensing. So to reach it, you can filter for the microlensing anomalies topic in the top search bar, and it will show you all of the related messages. So far, I've talked about all of the software from the perspective of a science researcher running a follow-up program. But of course, an essential element of this work is that the researchers should have access to suitable telescope facilities. So now I'd like to talk a little bit more about the software on the observatory side of the equation. As you know, time domain astrophysics, it can be quite demanding. Because we need to observe targets on a range of timescales from immediately through to months or even years. This can be very logistically challenging if observers have to travel long distances to a telescope. So it's enormously beneficial if at least some of the telescope's time is operated in a kind of queue-scheduled mode where observations are carried out by the operators. Then users need to have some kind of mechanism to be able to send requests for observations to the telescope for execution, ideally through some kind of software interface. And the observatory themselves then need some kind of scheduling system to figure out what to observe at what time. Now, this is all very powerful, but it does require some development work on the part of the observatories, which can be a bit of a hurdle. And so this was the motivation for LCO to create the Observatory Control System project. This is another open source software package, and the goal was to provide all of the tools that an observatory would need to run a queue observing program, with the researchers able to submit requests for observations rather than observing in person. And like the TOM Toolkit, it's designed to provide an out-of-the-box system, but enable users to then customize it to their needs. And to that end, there is extensive documentation available online. It's important to note that the OCS is distinct from a telescope control system. The OCS is really a communications portal with the telescope's users, and it also provides an observation scheduling system. The actual telescope operation remains unchanged, and it doesn't matter whether that's automated or run by a human in person. So the OCS package consists of a set of tools, and the first is a configuration database, which holds a complete description of the telescope and its instrumentation. And this can be configured to any observatory and any telescope, including single or multiple facilities, so it's extremely flexible. The package also includes a browser-based user interface, and this enables researchers to request observations and manage their entire observing program through the browser. And this also provides an API. So if your users are using a TOM system to manage their program, then it can talk to the OCS portal automatically. For the purposes of scheduling observations, it's important to know what instruments and what telescopes are available at any given time. And that information is held within the downtime database aspect of the OCS. And lastly, the package includes software that takes the requested observations that have been submitted by users and generates an optimized schedule to be carried out at the telescope. This is actually the same software that runs the whole LCO network, so it's very powerful and very responsive. But the OCS package is completely independent of LCO. The software is running standalone so that the telescope can operate independently. And lastly, but not least, once the data have been obtained by the telescope, the OCS provides an online data archive aspect, which can then serve the data to the researchers. And this aspect also provides an API. So once again, users can use a TOM system to download their data automatically so that they can process them and ingest the results again, and thereby closing the loop for an observing process. So that was a very quick overview of what the OCS package provides. If you are interested in learning more about this, our team recently hosted a hands-on workshop on these packages at the recent LSST in Europe 5 meeting, where we demonstrated how a user can run a TOM system and run their own OCS system and have them talk to one another. And all of the materials from that workshop can be found online at the URL on the top of the screen. And I'd also like to note that we will be hosting another hands-on workshop this coming January at the next AAS meeting. So if you are planning to be in New Orleans, then I hope you'll join us there. So I hope I've given an overview of some of these tools that we have for time domain science, both for scientists and also for observatory operators, and an update on some of the new functionality that we've added over the last year. All of our tools have extensive documentation online, so if you're interested to learn more, then please follow the links on screen. We also have a public Slack workspace where our team are available to answer any questions that come up, so you can join that by following the QR code on the screen. And lastly, I'd like to emphasize that all of these tools are really components in an ecosystem of services that extends to include the surveys, the brokers, the telescope, and many, many more platforms. And none of these services can accomplish the science that we want to do in isolation. So this ecosystem really works best when all of these services can talk to one another. And I will stop there, and I'm happy to answer any questions you have. Thank you.
Thank you, Rachel.
Thank you, Rachel. Are there questions to Rachel? Nada.
Hi, I have a question regarding the classifications that you quickly mentioned, I think early in the beginning. So my question is, do you get these initial classifications from brokers, information from brokers, or do you do your own light curve, initial classification?
Thank you for that question. Yes, we gathered that information on the classification from 3 different broker services. I think they were Alerce, Fink, and Terry's, I believe. And they are independently doing their own classification. So rather than repeat some of the work that they've done, we wanted to compare the classifications they were producing for the same alert stream, in this case from ZTF, to see if they were getting the same answers, and compare that for a large number of alerts. And the results were quite interesting. We developed the display tools, which we found very convenient, but we found that mostly they agree with one another. And the degree of agreement improves as time goes on, but there is a significant fraction of alerts for which they disagree. And I believe Rob Knopp in the Rubin science ecosystem is busy doing further work on that.
Yeah, and regarding this, I noticed, and I think all of the brokers that I've seen, they have this issue with classifying nuclear transients, especially TDs, and I saw that there was no TD mentioned in your group. So I was just wondering, I mean, since you take this from brokers, do you know in which category nuclear transient would fall? Because, it's either supernova, I guess, or quasar, but this is maybe just, based on the classification. But yeah, I've noticed that TDs are never, because it's hard, I guess, to classify them based on photometry alone, but yeah.
Yes, and this is something that really came out of that research project, was that there aren't many brokers that cover the full spectrum of known types of variability. Most of the brokers have been developed by teams that have their own specific science interests, and their classification schema reflects those interests. And I think we actually focused on supernovae because it was the one type of phenomena which multiple brokers provide detailed classification data on. I actually wanted the project to look at the classification for microlensing events, but there is only one broker doing microlensing events. So I think you have identified a clear problem in the broker services that are available at the moment, in that they don't necessarily provide a comprehensive range of classifications. And I believe the same is true in the TDE field. So I think this is an area of much future research is needed.
Thank you.
Any more questions? I have one, Rachel. We've met last week in Croatia for the LSST meeting, Rubin Observatory meeting. Could you just give a few sentence summary where the TOM infrastructure stands in the development of Rubin alerting system, and then also the follow-up?
Thank you. So the TOM system is really aimed at individual science researchers and teams of researchers, which I think the community will form around different science goals. So for example, the Dark Energy Science Collaboration is currently developing a TOM system for their particular science goals. And I know that the Transients and Variable Stars science collaborations are looking at building different TOMs for their science goals, each of which can be customized to the needs of those different communities. And similarly, the solar system science collaboration have a software working group which has a different set of needs. And that's why I think it's valuable for them to be able to customize TOM systems to their own needs.
Okay, great. So it seems that there is essentially kind of community-driven activities related with TOMs, and this is I think this is the power of TOMs, that they can be so easily customized. That's what we did actually with BHTOM, but we're trying to serve many research topics, but every community can build their own and tune to their characteristics and specifics. That's great.
That's my hope, yeah.
Okay, thank you very much, Rachel.
Thank you very much.
Yvonne, thanks for joining us. I'll take over your screen. Okay. And now we have Tom Esposito from Discovery of a Month. By accident, actually, I came over a website showing this amazing data collected by this network of small telescopes, and then I'm very happy to see Tom joining us on a very short notice to this workshop. So Tom, the screen is yours.
Thank you. Yeah, I'm very happy to be here, even virtually. All right. Let's play. Okay. Hopefully you're seeing my full slide.
Yeah, it's fine.
Great. Yes, so thank you very much for the opportunity to introduce you to the Unistellar network and what we're doing for rapid transient follow-up with our network of citizen scientists. So this is on behalf of other researchers at the SETI Institute, where we partner with Unistellar, a telescope maker and astronomy company, to do this work. All right, so just a brief overview of what we're trying to do, and that is become the fastest ground-based photometric follow-up network that there is, specifically for bright optical transients. You'll see why in a minute. But we have, with this partnership between the SETI Institute and Unistellar, we run a series of citizen science campaigns on various topics. And one of those campaigns we have dubbed Cosmic Cataclysms, and that is to follow up transient events. And so what our main goal is to be fast. We have telescopes all around the world looking at the sky every night, which we think means that we can get very rapid photometry for most events within an hour after their identification. For the best cases, we think within 5 minutes. I don't think we've quite gotten to the 5-minute level yet, but we've definitely gotten to within the 1 hour level. And of course, I think this goes without saying with this group, but a lot of the most important information about events, these transit events, gamma ray bursts, supernovae, etc., arrive in the first few minutes to first few hours. So that's why we really want this quick information. In addition to the rapid response, we want to have a coordinated long-term monitoring and do it with a relatively high cadence for the most interesting science cases. So this means multiple measurements per day over many months. And with LSST coming online next year, hopefully, then we want to use this network to guide new science and discoveries with all of the wonderful new transients that survey will provide. And to give you a bit of a timeline, we started beta testing this program in June of last year. The Unistellar Network for Citizen Science itself was formed in 2020. Full operations on the transients went into effect this February. That was with our automatic alert system and data processing, which I'll describe. And just recently in August, we added Astro-COLIBRI app notifications, which were discussed earlier by Fabian and Schussler, and we're really happy to be there. So let me just introduce you to the instruments that we're using for this for these observations. So Unistellar produces a commercial telescope, the EV scope, Enhanced Vision Telescope. It has a 4.5-inch aperture, 11.5 centimeters ish. It's a CMOS RGB sensor, so it's a color sensor in the full broadband optical, basically. And it's very easy to use. It's a smart telescope. For anyone, they just control it with the app from their phone or tablet. Very portable. Everything is built in. There's a computer on board, motorized tracking, automatic tracking, for example. And the cameras are different between a couple of models, but generally they have a roughly 40 by 40 or 40 by 35-ish arc minute field of view. Angular resolution, I think, is somewhere in the, well, it depends, but somewhere in the 5 to 10 arc second, full with half max level, depending on the data quality. And one of the key features is that the data from these telescopes, it's recorded on board the telescope, and then it gets automatically uploaded to us in the cloud over Wi-Fi, which is very easy for us to process the data. So what I like to say is that we get people to come for the enhanced vision, but stay for the science. So these telescopes are really primarily made for using, for showing beautiful pictures of the deep sky. There's some examples here, but they also have this tremendous scientific capability, which is what we're leveraging with this science program that we're running. The network is pretty big already and growing every day. So there's over 10,000 of these Unistellar telescopes around the world. And we've had over 500, so a small amount. 500 people have observed for science campaigns. That is people who have actually actively observed and contributed their data to one of our science programs. We also have a Slack workspace where we communicate with these folks. There's over 1,200 people following the Transient's work channel specifically. We have more than that in the Slack workspace in general. So just to give you an idea of how this is growing, I think this will play. So this is the number of users using their telescopes over time, from 2019 to 2023. And I know it goes pretty fast on the animation here. You can see we're adding people specifically, well, we are heavily biased towards the Northern Hemisphere. Unistellar is a French company. We have a lot of users in the United States and Japan, but we are expanding in the Southern Hemisphere as well. And that will be useful for LSST follow-up, especially. So this is where we are in 2023. And we have a pretty decent spread. I'd like to see more users out there, of course, especially contributing to science, but we are growing. Okay, so one of the things that we want to do is make it easy to become a citizen astronomer and actually do science with your telescope. One of the ways we do that is we provide all of the target information that an observer needs on one of three places. Actually, we provide information on all of these places. The Unistellar website, which is the white page here. We have our Slack workspace where we send automatic alerts to a channel that people can watch. And then the Astro-COLIBRI app most recently, where we can send a notification directly to your phone. And so all of the information that someone needs to observe a transient within about a minute of that transient being identified gets put into this table, for example, on this web page, the name of the target, what type of object it might be, when it was discovered, the magnitude, coordinates, and then these are camera settings on the right for the observation. And I'll come back to this link here, but there is a link that you can just tap and it will basically set up the entire observation for you in one tap. That brings you to the app, which controls the telescope, and there's a dedicated mode for cosmic cataclysms, very easy to use. And then we also process the data. So once those images are uploaded over Wi-Fi, again, with just a tap in the app, we can process the data and post a result to the observer within about 24 hours of the data being uploaded. We can do it even quicker. It only takes about 20 to 30 minutes per data set, but we only search for new data every so often. Let's see, I'm not going to talk about the pipeline that does the processing very much today, but it does follow a lot of the same steps that were discussed earlier in the previous talks. Essentially, we take raw CMOS Bayer matrix data, so this is RGB color images, and go from raw data, we do a dark subtraction, we do a plate solving to figure out our index coordinates that were actually observed. Then we will often stack the images to do photometry, and then we will create the light curve or the magnitude measurement or whatever we want to do analysis-wise. Okay, so the alert system is what I really wanted to discuss here. How do we get our targets? So every night, automatically, we run our alert system. Right now, we are looking at data from ZTF and the LRC broker. I am looking into other brokers as well, because as Rachel just mentioned, different brokers get different answers for different candidates quite often. So we get the data, the alerts, sorry, we get the kind of candidate alerts from LRC and ZTF. Soon we'll have LSST. We sort through all of those and filter them every night. And this is something that we do every 1 minute. And we look for a new, this filtering is done in Python, and we look for new candidates that satisfy our criteria. They need to be bright enough, above about 16.8 magnitudes for our little telescopes to see. We are focusing on supernovae right now because they're relatively straightforward. The classification from LRC has a probability for each target, and we just are looking for reasonably highly probable supernovae. And then I've started ruling out candidates with bright sources nearby because we were getting a lot of false positives. And so we will sort through that every night. It will automatically select targets, post them to the web page, that Slack space, and send a notification to Astro-COLIBRI. And then this all happens within about 2 minutes from the identification to going to the observer. So people can collect the data almost immediately. So just to wrap up with a few of our key results from the last, about the last 10 months or so. First was supernova 2023 IXF. So this was the Pinwheel Galaxy M101 supernova. Very exciting for a lot of folks. We published a quick research note in AAS journals of our light curve here on the left. This is the first 35 days of the supernova with Unistellar data. Our earliest detection was just 4.8 hours after the absolute earliest known detection. So we see here on the far left, there's some non-detections that we have before the supernova is visible. Then we started actually detecting it. And that was very close to the earliest known detection that at least that I have seen. And our data actually go back to 16 hours before the discovery epoch. And that's because we had people, observers, citizens, not even citizen scientists, just people with unistellar telescopes who happened to be observing M101, before the supernova happened and right after the supernova happened. So we were able to go back in time and get those archive data and do our scientific analysis on them, even though they weren't the data were not taken for scientific purposes, which is one of the really powerful things about this network, I think, is we have people looking in the sky every night, whether they're doing science or not. And overall, this was about a data point every 3.3 hours, and we were able to fit for the peak time in about an hour and the peak magnitude. And so that was early on, and since then we got 502 and counting V-band magnitudes since May. So these are all of our points here in color, and some ZTF archival data in a different band for reference. So we're seeing almost a very nicely filled out light curve here. Just two more. We're currently monitoring T Corona Borealis for its next eruption. This is a recurrent nova, about an 80-year period. It's extremely bright, and it's predicted to erupt very soon. Predictions go from as early as January 2024 to kind of later, more like June-ish 2024. Could be later, 25, 26. But we've started monitoring it just to monitor its variability, which it is a variable. It is in a variable phase before eruption anyway. And also we want to be the first to catch it when it actually does erupt. And one cataclysmic variable that we're looking at now, which is V6598 Sagittarius. This went off in around July 15th, I think. And we've been watching it ever since. You can see that it's getting fainter, but we can go down to about 16th magnitude at least for a target like this. I think we can get to V of 17 with a little bit more improvement on our photometry, even from these small telescopes. And we do see real variability here. So again, the gray points we're comparing to ZTF. We see a bump here, and that's seen in AAVSO data as well. So we are capable, and we have the precision and the quality to see real scientific features. So I'll just wrap up there. Again, we have this real-time alert system running. We go from identification of the target to observers potentially being able to observe within about 2 minutes. All this information goes to various sources online. And this is our website here for the alerts, alerts.unistellaroptics.com. We have 1,400 observations in 2023 alone from 177 different people worldwide. We process our data within about 20 minutes per data set, so results go back automatically to the observers within 24 hours. And then we're watching these various targets and a bunch of others for data, for scientific purposes. And for the future, I would love to add Gaia alerts. That's kind of high up on my list as another source of targets. Also want to tie in gamma ray telescopes, neutrinos. So we're working with the SNOOS team, gravitational waves, discussing with the Grandma team. And that would allow us to add more object classes like GRBs, AGN, maybe even fast radio bursts. And additional things I'd love to do is multicolor photometry. Like I said, we have red, green, and blue channels, and maybe even set up some robotic telescopes somewhere around the world. Okay, thank you, and that's all for now. I'll take questions if there's time.
Thank you, Tom. It's very exciting. I'm sure there's plenty of questions. Elena has one.
Thank you, that looks really cool. My name is Milena, I'm from Warsaw University. So my question is, well, I know you said that you don't want to mention a lot about the data processing of the thing, but I was wondering about the photometry uncertainties that you get. I always thought, because I've been using CCDs cameras, that the CMOS cannot really give us really nice photometry precision. So my question is actually also regarding the process. I mean, do you stack the data? And could you comment on that? Thank you.
Yeah, so I did gloss over most of that. So we actually can do pretty precise photometry, not as good as a science grade monochrome CCD probably, but pretty good. So so one of the, for example, this is a different topic, but one of the other science campaigns is exoplanet transits that we do. And so from that, I know that on a V of 13 magnitude star, we can do 1% photometry or better. So that's pretty small. That's something like 0.01 mags. For these fainter targets, when we get down to 15, 16th magnitude, we're in the kind of 0.1, 0.2 magnitude uncertainty level, and then it goes up from there. We do stack our data right now. We stack about 1 minute of integration time per stack. We can only take 4-second images. That's the longest individual image we can take based on the camera electronics. And so we stack those images up to about 1 minute, and that helps actually smooth out the multicolor pixel response in the sensor, so we can get kind of broadband optical magnitudes. We have seen actually doing photometry on the individual images and maybe even in the individual colors gives us better precision It just takes longer. So that's one thing we haven't implemented yet, but might in the future.
Tom Mikolajczyk here. I have a follow-up question to us. With this Bayer mask with RGB matrix, I suppose you are only doing aperture photometry because profile would be massively undersampled, right?
It depends on the color. So in red and blue, we are a little bit undersampled. In the green pixels, we're approximately Nyquist sampled. In the full colors, we're actually a little bit oversampled. But yes, we are doing differential aperture photometry here.
Okay, thank you.
Okay, thank you, Tom. I hope, well, we are all very excited, and I saw there is already some conversation going on Slack, which I encourage people to continue. So thank you, Tom, and I'll take over your screen.
Thank you.
There was someone on Zoom as well. I didn't see. Alexius, you had a question. Go ahead.
Yes, thank you for the nice talk. I was wondering, what is the shortest cadence you can obtain with your telescopes?
Oh, sorry, that was a question for me?
Yes, it was. Do you want me to repeat it?
It was the shortest cadence. You mean yeah. So the shortest absolute cadence we can do is 50 milliseconds. It's not very useful for transients. But the longest exposure time per image we can do is 4 seconds. So theoretically, our cadence would be 4 seconds.
Okay, I was wondering if you can apply your activities into the field of the lunar impact flashes, because short cadence would be great, and too many observers also would be great for such a project.
Yeah, sorry, could you repeat what kind of flashes?
Lunar impact flashes, meteorite impacts on Moon or on Jupiter.
Yeah, lunar, it's something we've talked about actually. We could do it. It depends on how much time we have to try something like that. Jupiter would be harder. That's pretty small for our telescopes. We resolve it, but it's not super highly resolved. So it's an interesting idea.
Okay, thank you.
Okay, thank you. And let's move on to the last talk of this afternoon with Fraser Lewis. And actually, it's not going to be far from the topic we covered, right?
Not too far at all. That's my last slide.
That's your last slide.
Yeah, which means I'm done, right? So, thank you. Good. Is there an advance?
Yes,
slide?
sure. Just press it. Put it on your finger.
I appreciate I'm the only thing standing between you and sunshine and beer, so I'm trying to make this as quick as possible. I'm Fraser Lewis. I'm from the Faulkes Telescope Project in Cardiff in Wales. I'm also part of FTP Europlanet, which is a company based in Germany. If I don't come back and remind you about that, please somebody shout it at me at the end and I'll explain a bit more about that. I'm also part of the National Schools Observatory, which is based up in Liverpool, and I also work for the Open University. You've already heard from Rachel today about LCO and the LCO network. Just to remind you, there are, I guess, 3 2-meter telescopes in the world that have an educational remit. I'm education today, that's where I'm coming from. I'm one of those, what were they, bad users? Not bad users, untrustworthy users. I'm one of those, and I represent several hundred more untrustworthy users. That's the Liverpool telescope there in La Palma, which I'm sure many of you are already aware of, and obviously the 2 Faulkes telescopes, which are in Hawaii and Australia. I've worked for several years in various aspects of Gaia and tried to sort of do bits and bobs with my colleagues. So here's an example of some work we did a few years ago. This is at the time, our postgrad, Sophie Bartlett, produced some resources as PDFs on the different aspects of the Gaia mission that were for teachers and kids, so to make that sort of aspect of the mission accessible to them. A couple of years ago, I was lucky enough, just sort of as we kind of hit COVID, to get some funding from the UKRI, the UK Research Institute, where I developed what was sort of decided to be a citizen science program, because they wanted citizen science programs, so that's what we decided to call it. It's based on data sets of type 1a supernovae from the Gaia Alert stream, and the idea was to get kids interested in doing photometry of these objects, so providing them with some very gentle data sets initially. They were using a browser-based piece of photometry called JS9. We heard today about DeoPhot and so on. When it comes to kids, we need to provide them with nice, simple software that is free of charge, that works on Windows machines and so on. So we're limited in what we can do in terms of quality photometry, but we still at least get them to go through the process. As part of that, they played around with some type 1a data, type 1a supernova data, and they calculated the peak brightness of the supernova, which allows them to add an extra point onto the Hubble plot, which allows them to calculate the age of the universe, which is not a bad sort of lesson for kids to sort of play around with. The ultimate aim, which we never really got that far, but we're still plugging away at, is to use things like Gaia Alerts, and obviously Rubin is coming online quite soon as well, and get kids to adopt their own supernova. If you have kids working on their own data, they are much more involved than if you're providing they're much more involved in the possession of their own data as it were. We were using the streams. We were talking about Stellarium, which is a piece of planetarium software. We thought about the idea of Python to isolate the most appropriate targets, and then we're using data analysis with a range of different things, such as Excel, Google Spreadsheets. It's really nice because, again, it introduces that collaborative aspect where kids can work together. They don't need to be in the same school or in the same country, same continent, or anything of that stage. Sorry, I skipped a slide. Those transferable skills. We don't want kids all to become astronomers because they'll all come along and make what's left of our funding anyway, so let's not do that too much. But we do want kids to buy into science. So the whole idea of collecting data, analysing data, producing results, that's the scientific process, right? So we wanted kids to do that. We were kind of sneaking some maths in. Kids don't always buy into maths, but they love playing around with astronomy and astronomical data. You can look at periodicity, you can look at error bars, logarithms, and so on. So we wanted to sort of get the kids involved in that way. We hit loads of hurdles and problems, which we're still sort of thinking about. The idea with citizen science is that you give them a simple task to do, but we want them to understand the science. The more science you put in, the more kids you lose along the way. So it's a bit of a balancing act. Installing software is always a horrible, horrible thing to do. And getting kids to work around with their own data rather than sample data makes things more tricky again. I will give you an example there of one we come across a couple of years ago, just to illustrate the timescales involved. This is data in 2018 that we took serendipitously, really, on this data set. My name's in there, a lot of the usual suspects are in that paper as authors, but draw your attention to the two that are circled there because they are based in a school in East London. So we were really, really pleased to get a school involved in a paper in that sense. Sorry, jumped another one. In the last couple of years as well, we've led a European Union Erasmus Plus program called La Skill, where we were developing lots of digital tools, lots of what we call demonstrators, which are lesson plans, and getting teachers involved in that. They were based in a series of different schools, 5 different countries around Europe. And we created what we call a demonstrator. It's a 9-page PDF or an interactive resource, if you prefer, which is using Gaia Alerts. So examining the Gaia Alerts stream and finding suitable targets, eliminating the targets that won't work, finding the targets that will, and so on. In this case, using supernovae. I would encourage you to have a look at that if you're interested at all in seeing the kind of educational resources you can do with Gaia. This year I've been lucky enough to just started sort of travelling again after COVID to work with around about 100 teachers in these two events. So there's both of these annual events we do with teachers. One is in the Canary Islands in Tenerife, and the other is in ISAC in Madrid, and working, let's say, with about 60 or 70 teachers face to face, and about 60 or 70 online. So I'm introducing them to Gaia, introducing them to what Gaia does. Not just Gaia Alerts, not just supernovae, but the mission as a whole. Why is it out at the Lagrange point? How does it transmit? Why is it going to run out of fuel or so on? Things like that. They're really important for kids to understand. I'm going to jump to one more thing, which is not strictly speaking Gaia alert, so please don't shoot me. I'd better read 2 slides and then we'll go back. I work with a group called GWIS Astronomy Modeling. We are a group of educators that meet once a week from USA, Wales, Chile, India, Colombia, actually the Middle East as well. I won't say where because we're not allowed to say where, but if you ask me afterwards, I'll explain. We are working on developing resources around using the LCO telescopes. So using the LCO telescopes for education, but not just imaging pretty pictures, actually doing some science stuff as well. As part of that, one of our students has been working with TopCat, which I'm sure many of you know, and have worked with in many aspects of things. She's created a whole lot of colour magnitude diagrams using TopCat, and you can see them there just as a way of sort of illustrating the kind of colour magnitude diagrams you get from TopCat. You compare those with the photometry you can get from a basic set of LCO images. I've put there, it's a paper in prep, I've put Martinez et al. Martinez et al. will mean nothing to you, I appreciate that. Isabel is currently 16 years old. She's been working with us for 2 years, and she is the lead author on this paper. So that's something that we're going to be shouting very loud about when that happens. I guess I apologize. I know it's not. I know it's Gaia DR3 rather than Gaia alerts. 2 more slides and I'm done. As part of the International Olympiad on Astronomy and Astrophysics this year, we had Gaia alerts used in 2 of the papers, in 2 of the projects. This was the Portuguese group looking at Type 1a supernovae. They produced a poster. If you're interested, I can share the poster with you separately, but just to give you a feel for the kind of things it's doing. Sadly, they didn't win a prize, but they were one of the sort of the groups that were well thought of for the work they did. And the other one is this group that worked on Gaia black hole candidates, looking at some of the microlensing events. I only really read this, I'm not expecting you to read the text in here at all, I only really read this today. They actually picked targets that are within constellations that are within their flag. So the Brazilian flag has these constellations, and they found targets in there that were of interest to them. So they went away and did some images there, and tried to take some images of the telescope, of these objects as well. That is it. Thank you very much for listening. If you have any questions, obviously throw them at me now or later in the meeting. Thank you.
Thank you. Thank you. That's cool stuff. Questions? Yeah.
So congratulations on all the projects. I was wondering if you do collaborate with some international bodies like International Astronomical Union or ECRO, this ESA, Member States Education Office for Education.
Yeah, so we work with a group called, sorry, should I grab the mic?
There's another mic.
So we work with a group called CESAAO that are part of the educational team at ESA in Madrid. We've worked with those guys for about 4 or 5 years now, so we work with them, and we have groups. I think I mentioned that Galileo teacher training program, and yeah, we usually communicate with the IAU people. And that reminds me about what I asked you to remind me about, which none of you have done as yet. Our group is Faulkes Telescope Project. We are in what's laughably known as the United Kingdom. We're laughable for several reasons, not least Brexit. We're being recorded, aren't we? So I shouldn't say more about it. But anyway, the point I was trying to make, we have a sister company that is based in Germany, so we are still sort of edging towards getting European funding and working with our collaborators. We're currently involved in 2 other Erasmus Plus programs with Germany, Greece, Portugal, and so on. Hope to continue to do that. So yeah, we work with as many different groups as we can.
Cool, thank you. Any more questions? Anything on Zoom? I can't see actually. Switched off. Now I lost it. Yeah, I lost it. If people on Zoom have questions, then just speak up. So I lost the windows. Where did they go? No idea. Maybe it means no, there are no questions. So thank you, Fraser.
Thank you.
Thank you all the speakers. But now it's Fraser was not the last point of the program.
So you plan to speak 10 minutes more?
Yes. No, it's a time. I think this is the opportunity. We should take a conference workshop photo right? I will apologize all the Zoom people, but we will not take a picture with you. We'll go upstairs, and because there is a beautiful view on top of this hotel, so go up to the 7th floor where we had lunch, and then higher than this, let's meet there in 3 minutes, okay? I will count heads, so don't go away. And thank you all for joining. I will stop this streaming and see you tomorrow morning.
See you tomorrow.
Thank you. See you.
See you.